a few words on just the general organization of the workshop, and then Konstanze will better introduce the content of the workshop. Konstanze is actually the work package leader for work package 3 in this project, and she will guide us through that. So first of all, let me welcome you all in Leuven. I'm very happy that you are here. Also very happy that I'm able to see you here in this very nice town. I hope you enjoy it as well. We are somewhat in the center, so if you have some time, definitely take your time and walk around a little bit around the center. I hope your hotel is also nearby, so there will be a little bit of time between the dinner tonight and the end of the conference. Might still do that. So there is also, as I already mentioned, apart from the food that you get here, there will be a workshop dinner tonight. The only thing you had to do was register. I hope you all kind of remember that you did. So you're welcome there as well. The address is on the program. Just use your Google Maps and you'll find it. It's like 5 minutes walk from here. You take your badge so that we can identify, and I'm sure that there's no homeless people that kind of join the dinner, although, you know, why not, nevertheless. I think those are the two most important things that I have to say. Maybe one further practical thing, you have a list of attendants. I will take one such list and let it pass around. This is particularly important for the people from the FarmConners consortium. Please sign. We will make sure that there is a copy of that available on the SharePoint, and this is something that you may use if necessary at your home institution to prove your presence here if you want to recover the cost from the project. Not everybody needs to do that, but some of us need to do that, so we'll allow that to happen as a practical thing. And I think that's about it for the practical side. So today we stay here. This evening we have dinner. Tomorrow morning we are back here. And there will be lunch again before we finish the workshop. Okay.
Yes. Hi, I'm Konstanze from SINTEF, and I am now here just to put this workshop into a frame for you. So this workshop is organized by the FarmConners project. It's a European finance project and it's a coordination action. And doesn't this actually work now? Okay. So this project was before summarized as answering the question, okay, wind farm control has been researched for more than a decade, but why can't you buy it? And this is kind of...
You can now proceed.
Okay. Yes. Anyway, so this is what this project aims for, is to support the commercial implementation of wind farm control. And yes, someone might say now, yeah, but Siemens just announced it. They announced their wake adapt system for wake steering, but this is just one aspect of wind farm control, and this is what this workshop is about. Because this project has several work packages, and the wake steering and wake control systems are one part, but this workshop here is about the market and integration, about work package 3. And that's why I'm standing here, because, as was said, SINTEF is leading this work package. And so, yeah, this is what this workshop is about. And if you look into that work package, we have 3 different objectives. One is to investigate the state of the art. So how are ancillary services working? How are the intraday markets today? And maybe how is it changing them? And also what potential value can wind farm control create in that? Another objective is to define a benchmark. The idea is to define market scenarios so that wind farm control strategies can be tested and their benefits should be quantified. And as the third objective, we have to also look into the design phase and if wind farm control strategies should affect the design. So these are not only the work package goals, but also the workshop goals. So we will have mostly talk about part 1 today, but we will look into all those cases in the next 2 days. And then I also wanted to introduce to you the organizational team of that workshop. So we had Johan standing here before. Then we have, of course, Ture from the EU, but also Kaushik prepared a lot, and Michael from Catapult, who couldn't be here right now. But of course also all the speakers that accepted our invitation are part of our team. And thank you for accepting the invitation and being here. And last but not least, because it's a workshop, all of you are part of that team here right now. And in preparation, I realized the K workshop has 2 parts. It's work and shop. So what we hope is that you work with us. So please engage in the discussions, share what you know, ask if you don't understand things, but also listen when other people are talking. And when you do all that work, we really hope that you can get something out of it and can do your shopping here. So you will learn hopefully something, have new ideas, new projects, make new friends, and maybe then you will really get commercial implementation of wind farm control on the long term, where this workshop is one step a little longer. And last but not least, I hope you also will have some fun. Yeah, so if you look at the agenda, we already managed the first and the second part right now, and we will now have 3 presentations before the coffee break, and we will start a bit easy so that also we as mechanical engineers understand the problem. So we have some presentations a bit more as an introduction before we get more insight into the markets. Yeah, and you all have this program also lying in front of you. Yes?
One question. I, as an electrical engineer, also understand the overall logical behind it. Just set my expectations right. When you said market structure, are you looking at a Nord Pool setup or any other European specific setup, or are you looking at a standard?
I think we will see different examples, but then there's also the idea to discuss the different setups and if we should look into different scenarios for different European markets, and also state right now and what's going to happen in the future. Okay, and otherwise, Nikos, it's your turn. Do you want? All right.
Thank you, and good afternoon also from my side. I'm Nicolaos Cutululis. I'm from DQ Wind Energy, actually sharing the same section with Ture, Gregor, and Kaushik. And I have to tell you that I actually think you can buy wind farm control, and you could do that, or you start doing that since 2003, when the first offshore wind farm, at least the Vattenfall system in Denmark for Hornsrev 1. But that's one of the points that I'll come back, because I think even in our sections, when we say wind farm control, we probably think of different things, Gregor and I, or Ture and I, or so on. So I think that control of wind power in general has many aspects and many directions of them. And when I was asked to talk a little about power transmission and grid connection of wind farms, it was a long time ago, I said yes, of course, and then I had to start preparing the slides, and I got a little confused on what I should talk about. So I ended up putting a lot of things together on how the electrical part, on the integration part of wind power is actually influencing or even driving the control of wind power. So, but I will try to talk a little broadly as categories, is a little about the wind turbine types, then show the grid connections and typical ways of grid connecting the wind power, and then also the power transmission of offshore wind power. And I'll get back to that. Why do I split the grid connection and the power transmission of offshore wind power into separate subjects? So, as a very brief introduction, or somehow to get this started, was about the at the end of the day, we put wind turbines out because we want to produce electricity, and we are very good at doing that. At least in Denmark is, as you know, the country with the highest level of electricity consumption that is covered from wind power. And we actually, it was just announced a few weeks ago, I think, that for last year we are very, very close to get to 47%. If you add up the very little PV power we have in Denmark and the solar, we've actually reached 50% of electricity consumption being covered by wind power. So how did we get there? How did we get here to this point? I think we did that in many ways, but if I try to be a little provoking, when you look at the actual wind turbines, how they really changed over the years, and I would argue, even with this kind of audience in the room, I would still argue that in many ways it hasn't really changed. Yeah, we have the same kind of wind turbines. That is, even if the tower is different like this, but you still have a typical wind turbine is a 3-bladed wind turbine and so on. So I don't think they have fundamentally changed over the years. Of course, before I get the weight of storm and things like that, a lot of things in the details have changed. Everything is much better about the wind turbines, but at least from a helicopter point of view, things have not changed very much. And there are very good reasons that this concept actually prevailed. But if we actually start looking a little closer to the wind turbines, you will see that at least in the more electrical work, we talk about type of wind turbines. And then we have 4 types of wind turbines. You can call them 1 to 4 or A to D. I think they are very equivalent. And then we have the first 2 of them, which were the directly connected wind turbine, type 1. Okay, or type 1 and type 2 wind turbines, which were directly connected to the grid. And it's from this perspective, the classification of the wind turbines is based on their connection to the grid. So they are directly connected to the grid, which means that the rotational speed of the generator is actually locked more or less to the grid frequency. And this was, or still known as the Danish concept, and they were very simple, reliable, and cheap kind of wind turbines. And I think they did a lot of work, and they're still doing in Denmark still a large part of the wind turbines installed are of this type. But their development, I think, stopped around or somewhere around 2 megawatt as a capacity, if I'm not very wrong. And then we moved to the variable speed wind turbine, where you can see that between the generator and the grid, you start having some more equipment. And this is the power electronics, which first were double-fed wind turbine generator, because the generator had double connection to the grid, one directly, the stator and the rotor is connected through power electronics. And today is the full-scale, full power converter, where the whole transfer of power from the mechanical to the electrical side is done through the power electronics. And this has basically allowed to decouple the wind turbine on the mechanical part of the wind turbine from the grid. And that's variable speed operation. It was, of course, it's beneficial for power extraction, because then you can optimize the power extracted at all the wind speeds, but also was important for load reduction. And today, I think virtually all wind turbines installed are variable speed, especially offshore. And I have to admit, these were slides from this summer or last summer in Cork, Invest conference. So it's already 12 megawatts and increasing the larger size of wind turbines. But I think today we are mostly looking at this kind of wind turbines. And the variable speed wind turbines, actually, when you look at their control, at least from my world, we have, of course, the pitch control that we know very well, but a lot of the control is happening on the power electronic side, where you have a generator side converter and grid side converter, and then you have the connection, and each one of them is controlled separately. And I would try not to go too much into the details, but you would try to control separately. This one is typically controlling the power extraction from the wind turbine or the generator or the drivetrain, and the grid side converter is actually trying to control the interaction and the exchange with the grid. And I will come back to that, because that's actually a big part of driving the control development. And of course, you can do the different control loops, and you can have the wind power plant controller, which will have to coordinate all that. And I'll have to say that it's still very not clear what is the difference between a wind farm and a wind power plant. We typically have this discussion also inside our department. What do we mean by a wind farm, and what do we mean by a wind power plant? But I think from a control perspective, that is not necessarily very different. So you can see here the different control loops. So you have you have typical control for the power electronics is a cascaded type of control. So you have cascaded loops which are more or less ending up of having a current control kind of loop in the converter side. Now, if we, I think I cannot switch now. How can I get the mouse here? Here. Okay. Now it's back. So, talking a little about the control of that, this is a picture I borrowed from another lecture, and it's not really talking about the power electronics inside the wind turbine, but the principles are very similar. So we have the different cascaded control and their control speed. It's basically dictated by the physics of the power electronics, the IGBT, the switching devices, which have a very fast, or they switch with a very high frequency. And then you typically have to design your control loops in a way that will be, of course, the outer loops. The outer you go, the slower the control should be. And we start from, I think, current controller is typically in the kilohertz or milliseconds range, and then you're coming up to faster or slower, typically between 4 to 10 times difference in speed of the control. And of course, the outer you come, then you have the slower controller. And one of the things that they are trying to avoid from an electrical perspective is to avoid the 50 hertz. But I think we are also coming down to frequencies that are relevant to the mechanical design. So power electronics control, I think it's a very fast control and cascaded kind of control. Again, from a power electronics perspective, I think if I would have to say what would be to remember about them when it comes to control is the fact that their behavior is defined by software control. So power electronics don't do basically anything if they are not controlled. Yeah, so they are not defined by metal, by their physical characteristics, but defined by programming rather than physics. Then the device, the dynamics are much faster than a conventional power plant. As I said, they are switching very fast, but of course they are not infinitely fast. They still have some switching time and physics limits. And also, one of the main design drivers of their control and protection is the fact that they are very small devices which have a very low thermal mass. So they don't like current overload. So they don't like, they heat up very quickly. So a lot of the control philosophy here is designed to avoid over currents, and to some extent also the voltage overload, but the current overload is very important. So trying to conclude, I think the power electronics have adding a very much more flexible behavior. So they're very flexible in the way we are controlling it, but they are limited by the physics. Control performance. Why power electronics, I think, are very important in the wind turbines. I think this is the case because they are, as I tried to say, they are not only enable very large wind turbines. I don't think we would see very large wind turbines with a fixed speed kind of technology. But besides that, besides enabling the very large wind turbines, I think they also greatly enhances their performance. This is, you're probably going to hear much more about that from Til Kristian in a few minutes. But today, a lot of the control development on the wind power plants and the wind turbines are driven by the grid codes in different ways or shapes or forms or whatever you want to see, because the grid code defines their how the facility connected to a public electric network has to meet to ensure safe, secure, and economic proper functioning of the electric system. And today, I think they put a lot of burden on the control performance from wind power plants. And that also shows that how the wind turbine plant control capability, at least from this perspective, from the electric part, has developed and is developing over time. So I think it started when we are calling grid following. And by grid following, it means that there is a grid already created. Somebody is creating the frequency and the voltage of the grid, and the generator in the wind turbine in this case has to connect and inject their current to the same with the same angle. And I saw in the program there's going to be a grid forming session tomorrow, so I will not insist too much about it. But these were the first part of the first wind turbines that were connected to the grid were having to some extent P&Q control. Not even that. Some of them be earlier than that. They didn't have those requirements, but. The simplest thing today they can do is connect to the grid and have some requirements regarding the power and active and reactive power control. But when you get becoming more important on the grid, your responsibilities also increase towards the grid, and that has moved the need for the wind turbines to be grid supporting. So what they're doing today, most of them or all of them, is to actually support and provide services to the grid, the ancillary services that Konstanze was also mentioning before. And that means that you're not only controlling you are able to control your active and reactive power, but you control it in a way or with the specifications and performances that are required by the grid. And of course, then you still require a power grid, but you can connect to what we call weak grid or a low source secret grid, and moving to a lower inertia grids because we have less and less mechanical parts directly connected to the grid. And I think most of the wind turbines today are in this area. They are required to do those things mostly in the middle. I think it's very few places, if any, that will have only grid following. But the more we are increasing the percentage of renewable generation, and wind turbines is the main one, we are moving to even more control requirements on the wind from the wind power plant. So we are moving what we call here the grid forming. So you are not only trying to control your power production or support the frequency of the system, but you actually have to control that frequency, create it and control that frequency. And that, of course, adds a lot of new requirements on the wind power plant. And of course, we are moving to what we call very low or zero inertia systems. And in some ways, we are already there. Some of the offshore wind farms are very large, from an electrical at least perspective, very large offshore wind farms connected via HVDC. So I think also at the wind turbine level, I guess my main message here is that the controllability or the requirements for control are becoming bigger and bigger, and a lot of them are actually driven by the grid requirements and less from the wind side or the production side. Now, moving on. When we talk about main elements of a typical wind farm grid connection, this is one of the slides we are using when we are teaching, and this is the representation of the wind turbine. We have the generator and the transformer, and then it's connected to the feeder, to the internal radial, and then it's connected to the main substation, and then connected to the point of coupling to the system. And typically, the more you are moving towards the connection point, the higher voltages you start. I think wind turbines are still built at low voltage inside. Then at each step you have to increase the voltage to the medium voltage, which is around 20 kV to 66 kV, and always the higher values, you will see them in the offshore environment more than onshore. And then, of course, you also have the largest one where you have the high voltage connection to the point of connection, which in my mind, when I talk about offshore, is to the shore point. So it's always increasing, and we have a lot of or significant amount of electrical equipment, which again is really outside the wind turbines in the wind farms. And I think this is basically done because you want to transport electricity. The losses are proportional with the current. So for the same power, if you have higher voltages, then you will have lower current that will run through the cables. If you want to see that in a different perspective, more graphical one, for offshore wind farms, you have inside the wind farms, so the wind turbines with the low voltage, then you have the voltage levels of the collector system of the wind farms, then you have the offshore AC substation, and then you have the transmission to shore. And it's the same here, you see the voltage levels that are increasing all the way to the shore. And this is very large piece of equipment that we are putting out there offshore. And I always use this picture as trying to show myself, but this is how an offshore substation looks out there, and it's a big piece of equipment with a lot of auxiliaries, a lot of other equipment that is included there, not only one or two big transformers. But then another thing that is actually influencing the grid connection of the wind farms, and this is the single line diagram of one existing of the Anholt wind farm in Denmark, one of the, used to be large, I think now it's medium to small, yeah, only 400 megawatt wind farm in Denmark. And you'll see that is the same, the wind turbines, the transformers, the common bus, but then when it hits the landfall, you have a STATCOM here, and then when it's connected, because it also has a land cable transmission before it's connected to the main grid, it actually has 4 STATCOMs. And STATCOMs are also power electronic devices, so they are in a way, from a very helicopter view, it's rather similar to the power electronics that you see inside the wind turbines, and they are used to provide reactive power compensation here for the submarine cable, and here to provide to meet the requirements that you have from the grid code. So again, a lot of equipment that is inside the wind farm, and it does impact its stability in the end, and its operation and control, which are coming from the grid side. Then if we move on the offshore transmission system, I've touched upon a little about it, because you cannot really separate always what is the grid connection and what is the transmission. But what we see is that we are not only increasing the size of the wind farms. I think the diameter of the circle here is related to the installed capacity of the wind farm, but we are also putting them further and further away from the shore. That means that your typical AC technology, alternative current technology, is start having some issues with dealing with that, because due to the reactive power, then the AC transmission, if it's not compensated or it has some physical limits over which can transfer power. And you can see an example here where you have the different voltage levels. You can see the higher the voltage, the distance, or the higher the voltage and the power that you can transmit, then the distance, the connection distance, is very influenced by that. And we have which is compensated, not compensated, or compensated on both sides, so both onshore and offshore. You can see that in any of these scenarios, the distance that you can use AC cables to the shore is actually limited. And of course, this is an academic example. It's not a real case scenario, but there is a lot of discussion, which is the break-even point, or where is the point where you can transmit using AC technology. So if we cannot use AC technology, then of course what we can do is move to the DC technology, and this one is rather similar. The picture here is similar as the previous one, where you have the wind farm and the offshore substation, and this is the role of that is, as I said, is to increase the voltage from the collector system to the transmission. But if we move to the DC, then we also need to have an offshore HVDC converter station. So then the power it's transformed to DC, and then you have a DC transmission to shore, where of course you need to transfer that again, or to transform that again into AC to feed into the system. And here we are discussing not only transformers and other auxiliary equipment, but another converter station, so another power electronic device that is put out there. And this one is also extremely large as a device. So we are talking about very, very, very large piece of equipment that is installed offshore. So if we look now on the single line diagram of a typical HVDC, you'll see that you have your wind farms, and this is an example of clusters. So you have several wind farms or wind power plants which are connected through the same HVDC transmissions to the shore. So you have, and each one of them has the offshore substation, and then you have the export cable, another substation here to increase again the voltage, and you have the DC transmission, or the DC, the HVDC link to shore, where you're going to connect it to the AC side. So a lot of electrical, or a lot of infrastructure around only the transmission part to the shore from offshore wind. And this is, of course, done typically for offshore wind today because that's where it makes economic sense. But if we're really going to build a DC backbone onshore, it might not be very far away in some future to see something similar on the onshore grid as well. And of course, the discussion between AC, DC, it comes down to cost. You have some physical limitations. So as I said, that you cannot transfer power over infinite large distances with AC connection, but if you want to choose between them, you have something like that. This is a very shown graph, I think, in many forms and shapes, but the main idea is showing that for each of the technology, the DC is the blue one and the AC is the gray one. You have some initial costs, which are the equipment costs, the substations, the converters, and so on, and then you have a cost, a variable cost, which is depending with the distance. And the AC cost, you see, it's the initial cost is lower, but then it's much steeper when you with the distance. While for the DC is the other way around. You have an initial cost, and then it has a variable cost, but it's not as steep as the AC one. And of course, everybody is trying to find this sweet spot where is the break-even point between the two technologies. And I know the developers always look into that, and you can have different ways of doing that. So if I try to say what is the best solution between those two, I actually think today is far from clear to what we should do. And we have a lot of examples of that. We have the HVAC, high voltage AC connections, the standard one, what I was talking about. This is just the Hornsrev area, but I think the vast majority of wind farms today are connected through HVAC. Then we have a number of HVDC projects, mostly today located in Germany, where you have the clusters connected to the shore through HVDC. But then we also have a number of in-between things, I would say. We have the HVAC with compensation. This is hosted in UK. So if you remember, as I said, you have a certain distance after which you can use AC connection. So one way of doing that is basically splitting it into two. So you have the wind farm, the collection, and then use an AC cable, and somewhere midway you put an offshore compensation, and then you can use a second AC connection cable. So this is the HVAC with compensation. That is the largest offshore wind farm today. The Hornsea one is connected through this technology. And then we have the Krieger's flag one, the combined grid solution, which is very, 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 very interesting solution that was decided, and it's implemented. And I think I actually saw yesterday, I think the first test of the converter station in Germany has happened. And here it's unusual because you have AC connection all the way here from Denmark to Germany, and here you have a back-to-back converter to break the two synchronous areas. So you have a lot of AC cables, and they even have different voltage level. The Danish one is 220 kV, and the German one is 155 kV. So all kind of solutions on how to do this power transmission to shore. Of course, there are a lot of reasons for that. Some of it is the interconnector and the market part. I think probably we'll hear something about it in the market talk a little later. But from a technical perspective and a control perspective, each one of those has its advantages and disadvantages and complexities. And if we go even further, we are also talking about meshed grids in the North Sea. So we will have a meshed grid it's a grid where the power that is generated can move to the different points with more than one path. So you have different ways of moving the power from a point to A to a point B. And I think that's typical for our transmission systems onshore. Or going even further, we are talking about building artificial islands in the North Sea to accommodate, mostly to accommodate very high numbers of offshore wind. So again, my main message here is that all this grid connection part is not something that is solved, but it's something that is still very much out there for debate, and it's people are still looking for the best solutions for that. Now, trying to summarize a little, I hope I'm not too bad with the timing. From a control perspective, I think the grid connection and power transmission are adding complexity to the whole system. If you see the wind farm or the wind power plant as a system, the grid connection is adding a lot of complexity to that system. Then the HVAC connected offshore wind power plants are, from an electrical perspective, a weak system, long cables, which also means that they are maybe not prone, but there is a good opportunity, a good chance that you will have instabilities there if things are not properly controlled. I think I have an example of that later. And then I think we already see that from the HVDC connected offshore wind power plants, which are very complex with low, if not zero inertia systems. So another interesting aspect from a control perspective. And then finally, I think if we talk about the wind plant and farm control, without even including the part of the flow modeling and control, only looking from the electrical part, you actually have to supervise and coordinate a very large number of control loops. And I used Dogger's Bank as an example where they're expected to have around 100 wind turbines per plant with 12 megawatts each, which will mean more than 200 individual cascaded control loops, as I said. And all these loops will have to be coordinated by a wind farm control or a wind plant control. And now just to show you an example how this electrical infrastructure and this complexity in the electrical infrastructure can lead to issues. This is the event in August last year in UK, where because of the harsh weather, a fault occurred. Yeah, there was a lightning strike on an overhead line, and then of course that line has to be disconnected until the fault was clear and then connected again. And of course, when you disconnect that, you see a voltage dip. So here is the voltage profile, which is from the nominal, the rated one, how much the dip was seen in different points in the system. And in one of those points, you had the Hornsea offshore wind farm, which was connected there, and which initially, I will not insist too much on the graph, but I wanted to make the point here that while it started behaving what was expecting to behave under a fault right-through condition, then for whatever reasons, probably, I think what came out in the public was that there was not a proper coordination between the different control levels, starting from the wind turbines all the way to the shore, to the STATCOM that was installed in the shore. You start having oscillations of reactive power, and at some point, the wind turbines, because they were seeing high currents, as I said, current is something they are really sensitive to, high currents, then they shut down to protect themselves, to not burn the power electronics. And this is what, to a large extent, helped in create the frequency event that we saw in UK in August, and which of course became such a big issue because it was London and a lot of railway went on and so on. But unfortunately, in this case, wind power sort of did not behave as expected from the grid code perspective and disconnected a large amount of generation, which led to the frequency event. So sorry, I didn't say that. This is how the frequency developed into that part, and because it start falling, and then when you start losing more generation, it fall down to a level where they actually had to start disconnecting load to make sure to try to limit the drop of the frequency in the system and limit a total blackout of the system. And at least what came out in the public, this is part of, this was due to the instabilities or the oscillations that they had in the electric systems due to not properly tuning the controllers and the interaction between the wind turbines and the grid connection point. So I think, sorry, I had too much. So my final messages, I think, from this presentation, what I would try to bring here is that a significant part of the control aspects in wind power are coming from or are due to the grid connection and the codes, and this is only increasing. I think more and more of these requirements are coming out, and we should remember that the more wind power, the more successful it becomes, and the more wind power we see in the system, actually the control responsibilities towards the power systems will keep increasing. And yeah, electrical infrastructure and transmission system offshore wind power are very complex, and they actually drive technology development. I think a big part of power electronics and VSCs and HVDC technology is driven by wind power and offshore wind power in general. And I think a lot of the times the electrical and power engineers tend to forget a little about the mechanical aspects of the wind power, and that's probably a subject that will become more and more of will become more and more, we have to coordinate more and more in the future when you have all these control aspects, because at the end of the day, behind the power electronics, you do have what the people are calling the largest dynamic rotating machines in the world, which I like the sentence very much. So, and finally, I wanted to end up with this image, because I know you have tomorrow, Ivan, talking about 450 gigawatts of offshore wind power. And if that happens, and I think to some extent it will happen, whether we like it or not, this will mean not only a lot of wind turbines, but even much more electrical infrastructure that will come with it, that will have a big impact on how we control and operate our offshore wind power plants. Thank you.
Very fine. We have about 3 minutes for questions.
Yeah, so first question maybe on, I like this example of the Shadano sea wind farm. Is it an issue with wind farm control or an issue with turbine control? That's, in your opinion, that is, I mean, the question is, what is wind farm control, right?
I think it's very hard to say, but it's also very hard to make a very clear distinction between the two. It did come down to the wind turbine control, because the wind turbines protected themselves. So we will typically come down to the wind turbine.
Right. I guess from my perspective, I guess I would say wind farm control is something when you try to control or have to control the collective behavior. So from flow sides, which would be my side, obviously you need a lot of time or enough time for them to behave collectively. How is that on the electrical side?
I think it's exactly the same, because I think maybe I didn't say that, but actually wind farm grid codes are typically, let's use this one, are typically telling you, okay, this is the HVDC one, but let's use that as an example. They're telling you how it should behave here, or the connection point. Okay, the grid codes don't really talk about the individual behavior of the wind turbines, but they talk about the point of connection. So in that sense, the one that should make sure that you have the required performance here is the wind farm control, which in this case means the wind farm control of the electrical part. So we are trying to control the exchange with the grid in that point. Yeah, in that sense, the definition I don't think is different.
No, but you would be much faster, because I guess whatever's happening in the internal grid is probably going to be kilowatts.
Yes. Yes, it is faster. I try to give the timescales here just to bring that to the table for the discussion.
Obviously, the example was called at a wind farm. How do you feel other wind farms sort of next to the grid, they have played a role in helping the system restore, and what kind of barriers do you feel would prevent wind farms from providing that service? Because you've got very large problem frequencies, there's something that other wind farms next to the grid have done.
I think they could. I mean, first of all, they should have behaved to help with the flow right through. Yeah, that didn't happen, and I think at least in the case of the Konstanze one wind farm. But I think wind power plants are, well, to some extent today, being part of the frequency event, because the problem is you have a voltage event that translates into an active power event and translates into a frequency event at the end of the day. So I think they should operate more, and that's where the wind farm control on the flow part, on the active power, could play a bigger role. But I don't think in this case a lot of them participated into that, into the primary.
So it has some role help in this situation, not just by controlling that particular wind farm, as the role to play for other wind farms.
Yes, no doubt about that. But I think that's more of a sort of a market structure today than a control issue. Or it's also a control issue, because we like to push it, but when you go down out there in the real life and you start seeing the example of answers, profiles and how they answer, they don't look always like in our simulations. Okay. Thank you.
So now we move to a bit more boring subject of grid codes, but it's still very relevant and necessary. And I gave it the subtitle Beyond Maximum Power Tracking, because this is basically everything besides what a wind farm normally should do, produce power. So I give a brief introduction, and then we'll talk about a bit about the evolution of grid codes to make it a bit more exciting. And then I go through a range of different requirements. So introduction, the grid codes are the technical specifications for any facility. It's not about wind power, it's about anything. But of course, I'm focusing only on wind power. And they should just ensure to define rules that the grid operation is stable. And it's normally generalized rules, but there's always exemptions, and there's exemptions of exemptions. So it can be quite tricky, and they are available in at least most countries. So this is a good reference to know what you have to do. And these grid codes help to make the process of developing such control loops, as we heard in the last presentation, it's easier to design them if you know what you have to do. But there's also some issues with grid codes, and this is really a challenge. It's a legal regulation documents, so they can be quite hard to read, at least for us. Maybe lawyers think they're very easy to read and very intuitive, but at least most of us do not. And they can have very many pages, so it's always a problem to cope with grid codes. And it can also be things that are unclear or missing. So often it helps more to read summary documents that translate the grid code into a more technical format. But those again can be outdated because grid codes evolve. So in general, it's a tricky subject to deal with. And then ancillary services, just to make the separation clear, that is providing more than is actually asked by the grid code. Grid code tells you have to do this. Ancillary services, you can do this, and you get paid for it. In the grid code, you have to do it, otherwise you get fined for not doing it. And the fun part is one control feature could be in one region, it could be a required grid code thing, but in the neighboring country, it could be something you get paid for doing. So there's no uniform approach. But there is a common division, which is not always true, but it's just a general rule of thumb. Grid codes often ask for the capabilities, that you can do something. But it's just you have to be able to do it. You don't actually have to do it. But once you do it, you provide a service, and that can then be a market behind it. But at least for wind power, this is still it's not really established. It's still way up. Because how this all started in the 80s, we saw the old wind turbines by Nicolaos. When they were built, there was almost no requirements. They were so small, the grid operator didn't worry. Just build something, do it as you want. And if there's something going wrong, just disconnect. We don't worry. But then in the 90s, wind power gained momentum and picked up. And at least by 2000s, there was a large-scale deployment of wind power plants, but still following rules that were designed for a first prototype small turbine. And this is usually never a good situation. And we found out in 2006, then this is what the European grid looked like. There wasn't a grid, it was three. And it split into three parts. That was, people believed they had it under control, but they found out, no, we don't. And that was quite a big incident, probably the biggest incident in the European electricity grid ever, or after World War II. It's important to say this was not caused by wind power. So don't blame wind power for it, but they became more critical due to wind power. Because wind power plants were doing really stupid things. There were regions with a too low frequency, and they would disconnect and make it even worse. Another region, there was over frequency, and they would push in full power to make it even worse. But no one could blame the wind power plants because they were doing what they were told to. The rules were bad. And this really demonstrated that the requirements need to change. And I think from 2006, the development of grid codes for wind power really kick-started. And another development is the geographical distribution. This is an old map. By now, it's much more. But what am I doing? These dots are wind power plants. So the renewable energy and development has skyrocketed the number of power producers. And this really put on the focus that if you don't have 10 big power stations, but if you have 10,000 small ones, you need to have standardized rules. You can't talk to every power producer. So this really made the case-by-case decision economically inefficient and also boosted that grid codes again so important. But then there was a lot of different grid codes, but this has happened on the national level. And for the island systems of Great Britain Island, this is not so bad, but at least for continental Europe, it's quite unfortunate that every country was basically cooking its own meal. So until still today, there's a lot of difference between the countries. And this is very hard for anyone in this room, because when you develop wind farm control for the future, you don't consider a specific country. It's in general. But there is no in general for grid codes. It's very different from one place to the next. So it's really a problem, and it's a challenge for any international actor, which is all wind turbine manufacturers. And there is effort to standardize this. It was the European Commission that actually pushed the European Network of Transmission System Operators for Electricity, ancillary, that this has to be harmonized. And they started a process and wrote the European grid codes, which was published in 2012 already. And there's now this program, they put a framework, and all grid codes should follow within this framework. But the trick is the framework is so wide that basically all grid codes already fit without any changes. But this is also natural, because the ancillary doesn't have the authority to go to a specific country and tell your grid code is bad, we have a frame, you have to change them. They can't really do this. So this is all basically finding the smallest possible compromise. So it's a step towards uniformity, but still it's only a step, and it's still challenging for us. But now going more into the specific requirements. Operational range, I think I'm going a bit fast on this one because it's not so relevant for wind farm control. But the grid codes define a range of frequency and voltage, should be 50 Hertz and should be 400,000 volts, or depending on voltage level. But there's a range around it which you have to accept. But this is not so challenging for the wind turbine. This is really more an issue for the power electronics. The variation in frequency around 50 Hertz, that's not much of an issue for the power electronics. They can do it. And but so here again, it's different for all 5 synchronous areas of Europe, which we've seen on the map. So also here it's very tricky. These curves look all different. But what I wanted to say, it's more tricky on the voltage part, because this fluctuation of the voltage, which has to be accepted in continental Europe up to an hour, a range of 25%, is a problem for the power electronics, because if the voltage goes low, your currents go up, and we have heard a lot that that's a problem. So in case you're operating somewhere down here at this voltage, your converter is already close to its hard limits before something else has happened. So this basically forces to overrate your converters to be able to cope with this. And the question is then how much do you overrate? It's not. Because the overrating converters is never for free. And also a funny example on unclear grid codes. These curves are taken from this European code for this European framework. And they gave you 2 sets of requirements, one below 300 kV and the other one above 300 kV. And this is just our interpretation, but they never specified what is at 300 kV. They just said above and below. But 300 kV is actually a voltage level. So this is just another tricky one. But then more interesting is the reactive power provision. We have talked about this for voltage support. That is not the grid following, but the grid supporting control. This is a main feature. This reactive power capability is essential to do this. And normally, it's not real truth, but it's a guideline that works for all realistic situations, is feeding reactive power into the grid is increasing your voltage, and drawing reactive power is decreasing the voltage. Grid codes, they require that you can do this. And if it's actually activated, if it's really used, the capability, that's a totally different question, but at least there's a requirement that you have to do this. But for the modern turbines, this is also a part which the power electronics do. It is not the turbine itself. Then there's different characteristics. How does your reactive power capability function as a function of the grid voltage? And how does it affect as a function of the power? And also here is many tricky aspects, because there can be large variations, and there can be even more problems that if you have already a high voltage and then providing reactive power would even increase your voltage even more, but that's something that you normally would not want to do. But grid codes can be formulated in a very general way. You have to be able to provide reactive power. So then in the end, if you follow the requirements, you have to design in a way that you can do something which is difficult to do, but it's meaningless. So you will never be asked to do it, but still you have to prove that you could do it. So there's many challenges regarding this grid interface, but I will pass them fastly, because this is not so influencing the control of the wind farm. This is really more the electric equipment side that we heard a lot about, but I don't want to go too deep there. But then the next part is the active power frequency response, and I think I want to focus more on this, because this is really influencing the wind farm control. And the grid frequency, that's our power balance indicator in the grid. On the frequency, we can read where we're at. Too much power, frequency goes up. Too little power, frequency goes down. And the grid codes define this active power frequency response, which is just the automatic adjustment that you help with the grid supporting control to stabilize the frequency. And the grid codes, they split in two parts, which is good, especially for wind power, it's very relevant. It's the over frequency and the under frequency part. And for over frequency part means we have too much power, and this is something that wind power can really easily do, because we need to reduce the output if necessary. And in theory, this gives economic losses, because once you reduce, you extract less power. But that's not really an issue, because it's short duration, it's very rarely. So the total energy lost is tiny. But it gives a real high value to the grid in that you reduce the power in case of overfrequency. And this is one of the things that hasn't worked in 2006, and where the 2006 event would have been much smoother if all wind power plants would have had this feature. And the very nice part is that wind turbines are so good at quickly reducing the power. I don't know exactly how long it takes to shut down a wind turbine, but it's quite fast compared to a coal power station or a nuclear power station. So here it's really wind power plants have an advantage, and I hope that this is accredited more in the future, that this capability is used in a better way. Like even in Germany, that's maybe the worst example. There have the renewable power is prioritized. So even though wind power would be the best suitable candidate to reduce, they rather force someone else to do it because they want to have the wind power online. Which just makes sense from a political point of view to support wind power, but from a grid operation point of view, doesn't make any sense to force someone to do it who actually is very bad at doing it. But at least this is what wind power can do very well. What's more difficult is the under frequency part. Frequency is too low, we need more power. And what do we then with our wind power plant? We need to increase, and this capability is required by the grid code, at least for larger wind power plants. If you have a single turbine, generally requirements are not so rough. But for wind power plants, you have to have this capability, but you need to decrease your output on a continuous basis. Because normally this is not possible. If you track maximum power, you're either at your limit or you're at the limit of what your actual wind speed gives you. So with a normal, I would say, normal wind power control, which maximizes energy extraction, you could not do this. So to really supply this feature, you would need to continuously demand your output, and you lose a lot of power. The capability exists today, but the question is then, is this meaningful to do? Because you on a continuous basis extract less than you could have extracted. And this is an interesting topic. Does this economically meaningful? Because not extracting power which you could have extracted gives you economic losses. And this is great in case wind power is curtailed. This is what they have in Ireland. They have put the hard limit to say wind power is not allowed, I think at the moment, 70%. Yes, 70. They change this all the time. At the moment, you cannot have more than 70% of wind power. So if it's a windy day, they could have more, they curtail. And once you have curtailed for other reasons, like network loading restrictions or the stability considerations in Ireland, then you have curtailed wind power, and then you have a great means of providing the upward frequency reserves without any problems of losing energy by not harvesting it. This case appears in Ireland, but it doesn't rarely appear on continental Europe or other regions because the share of wind power isn't big enough that you would need to curtail it to start with. So in other cases, if you would want to provide this frequency response from wind power, the frequency reserves market would need to cope with these economic losses. You would need to earn more money by providing service than you lose money by not harvesting. And this basically you can only do when there's no cheaper alternatives available. And this doesn't work when the price for electricity is high and the price for the service is low. And this is the situation we actually have mostly today. This is when thermal power plants operate to create electricity. They're online, they operate anyhow, and they are better at this. So this is the situation when the wind power, even though it has this capability, but it's economically not viable to do it. But looking more into the future, this can turn around with a low electricity price and a high reserve price. And in this situation, normally, if wind did not support this service, you would need to run thermal power stations, even though you don't need the electricity they make, but you just need to operate them so they can be service providers. And in this case, the service would get really expensive. And this is when wind power kicks in. So looking into the future, I think this is a very important feature that we will see. The importance will grow over time with increasing share of wind power. And that is not even only happening once, but it's like happening twice at the same time because there's two reasons. Because more wind power gives you less other power plants that could provide the service, and this is one issue. But the second is wind power itself increases the need for frequency support because it's variable and there's forecast errors. So the need to integrate wind power into the support grows over time, and it will become a complete necessity in the long run. Yes, that was the active power frequency response. Time, yes. Okay, next is fault right through, as Nicolaos has shown also this voltage dip that caused the problem. The fault right through requirement tells you to, even though you have this deviation of the voltage, if it's just for a short time, you have to be able to ignore it and keep operating. And this is what did not work with the wind farm, as in this example. And this was developed this requirement for fault right through was developed to actually prevent this from happening. And even though it doesn't always work, it works often, and it has really improved grid stability a lot. This is a plot from Spain. This is the green curve, shows the number of wind power plants that do not have this feature, which increased with the number of wind power plants, and then they made it obligatory to have the feature. And blue is in a simple way to say, the issues caused by it. So it was the blue just disappeared to zero. It's a quite simple idea. It works well and it's very important, but it's the tricks lie in the detail when you get these interactions which you did not expect. And then, as he said, it was the turbine protection that kicked in and shut off. And that's always something that will happen, because there's no way any grid code or whatever could overrule this internal protection of the power electronics. They're really sensitive, and they cannot handle overload for any relevant time. They overheat in a millisecond. But this fault right through is mostly relevant for under voltage, as in the example. The grid codes, they specify curves of a shape of a voltage dip. This is 100% of voltage, and it gives a time specification. And the European grid codes give you a range between the red and the blue curve. And then any single TSO could draw a line in between somehow. But the range is not so big, so at least here we know pretty well, even though the grid codes are very different around Europe, but at least what kind of voltage shape we need to withstand for a wind power plant, we know quite well. And if we just take the red one, then we're on the safe side, then it's good. So this is the good part. We know very well what we need to withstand. But there are some small regional variations. And this is maybe the most prominent grid code feature, which has been discussed a lot, and which always has helped a lot. But then again, now we come to the details, and it gets tricky because there are some definition gaps. What is the maximum fault voltage is 0.85, minimum operation voltage is 0.9. What's in between? It's not written in the grid, at least not in the European grid code. So here again, you would need to check every individual code. So then this is creating really a hassle for any of us. Also, over voltages are not specified Europe-wide. This is really region by region. If voltage doesn't go up or down, but it goes up, what do? We don't know. But even worse, asymmetric faults. Majority of faults is asymmetric. That means you have three phases, but not all are affected. It would be really essential to have clear definition. It's highly relevant for stability. It can lead to, like a single phase short circuit can lead to overvoltages. It's really relevant, but also this is not specified on the European means. And because they couldn't agree on anything, because there were so large differences between the countries that it was hard to define the frame. So again, this is one of the topics where it's really hard to just look into the European grid code and know what to look at. It makes it complicated to deal with. And also sequential faults, if you have a fault and then it brings the turbine out of normal operation, and after the fault it needs to return. But what happens if the second fault appears before you're already back to steady state? This is also a challenge, especially for solar panels. They don't have any real time constants, they don't care. But for a wind turbine, this can be a trick if two faults happen too quickly. And also, even if it's not two, if it's many more. This is also not specified. So here it's really unclear what design criteria we should use for the wind farm and for the control. And actually, this is also relevant in Australia. A few years ago, there was a blackout caused by sequential faults. So it's relevant, but still regulation is lagging behind the technical realities in the grid. And also a tricky one is, if there's a severe fault, which is not for a short duration, but it lasts longer, what do we do? And there are actually grid codes disagree on, should we allow to disconnect, encourage to disconnect, oblige to disconnect? So again, it's hard to know. actually, if we want to have a wind farm control that works Europe-wide, it has to be able to do everything. But we don't know. And then this is maybe the most difficult. The grid code gives us this shape for the voltage dip we have to withstand, and for this we have to maintain operation. But yeah, maintain operation and do what? And this is problematic because the behavior is not specified on the European level. It just tells you have to stay connected, and it gives you connected and stable. But in theory, we could say, okay, connected and stable, we do zero current. We operate stable and connected at zero current, but that would work, but in the end, this is the same as disconnecting. If you have no current, you don't do anything. This is not desirable, but it's within the specification. So the behavior, what should we do while we withstand the fault? This is again different from TS0 to TS0, and there's big differences. And this is also very hard for the control design because different specifications require different things. But then what do we really do? We have the fault. We don't know how to behave. At least there is some common aspects on how to behave during a fault where grid codes mostly agree. And this is that you counteract the voltage deviation with reactive current. So depending on if it's over or under voltage, you try to support the voltage to bring it back to normal. And afterwards, you recover to pre-fault operation. But then the trick lies again in the fine print. If we have full active current, maybe even the voltage was a bit low, so we were at the 110% of the current already to compensate for the lower voltage, and then we have to supply reactive current support at the same time. While we already at full active power, our converter doesn't give more, so we run into limitation. What do we do then? We have to do active and reactive at the same time. In some regions, we have to prioritize one, and in other regions, we have to prioritize the other. And this really affects the wind power plant itself, because once you have to prioritize the reactive power means you cannot have the active power anymore. And that means you cannot get rid of your power, which you actually harvest from the wind, at least not for some time. So then you have to get rid of that energy in some means. And also the recovery, there's a big difference. In Ireland, they say you have to recover as fast as possible, while in Tenerife, they say you should recover in a slow and nice way. But this slow recovery also means that if you want to not change the pitch of the wind turbine, that you, for a longer time, you harvest energy which you are not allowed to push into the grid. So you need to go somewhere with that. So this is also a non-heterogeneous picture. But in Ireland, they have a quite nice example. Also with this gap between grid code and ancillary services, they give a minimum response, which is specified in the grid code. But if you can do better than that, you can get paid for it, if you can recover faster. And this is the Irish example, but I believe this is the future, and we will see more of this in other places. Other places just don't have so much wind power yet, so they didn't need to implement such a thing. And then also possible future requirements which we don't have yet today, but we might see as inertia will be a challenge to the grid. Nikos mentioned it. Inertia stabilizes the grid as an energy buffer. It's just like the inertia of the wind turbine rotor, which basically stabilizes the rotational speed. But the grid inertia decreases. Okay, same does the rotor inertia for wind turbines. There's better constructive, better materials. So I'm sure a rotor with the same blade length today is lighter than it was 10 years ago. But this is still kind of like nice and smooth decreases of the inertia of the wind turbine rotor. But the grid inertia decreases much more than the wind turbine rotor inertia, because you have this energy transition where many power stations just get replaced by solar panels that have zero rotating nothing. So the grid inertia is really much more on the way down than the rotor of the wind turbine inertia would ever be able to go down. And this low inertia can cause fast and deep fluctuations of the frequency. And this is not good. And so this means we need to support the frequency in a different way than we have ever used before. Frequency support has existed for 100 years and it worked, but the old methods, they can't hold up to the future. And basically there's two ideas. One is we have fast fluctuations. We just need to be faster in the control. And this is something that wind turbines actually can do quite nicely because the power electrons, they are so responsive, much more responsive than a synchronous generator. But the idea too is not enough inertia, we just emulate inertia. And this is also a nice topic, that you fake the behavior of inertia by control. But for any of those means, we still have the same problem mentioned several times. The converters they lack short-term overload capability. And especially in these frequency moments, it could be that we just need a bit of extra power for 1 second, and it's very expensive to buy a bigger converter for this 1 second. But there's actually no really way around it, because you cannot overload it just for a second. While all classical electric machinery, transformers, cables, everything of those, overload them for a second is no problem. So also for this frequency support, we will see changes in the requirements and in the services for sure. And the other one is the high wind extended production control. Normally the wind turbines shut down during a storm, which is nice, but in the long run, if you want to run the system based on wind power, we can't just keep doing this shutdown. Because the density, like the geographical density of wind power gets so large, and so when a storm hits, you lose a lot of production within a short time, because all the turbines in the region will see the same storm front in a quite short amount of time. So then the solution is that you just cannot switch down the power, but you ramp down. And this already exists today. Like I know Enercon has the storm control, but others do have a similar feature, that you don't have a hard switch off the power. So this technical feature is already there. It's not yet really required in the grid codes, besides in Denmark, at least to my knowledge. Maybe someone else has already implemented the requirement, but I'm not aware of it. At least the Danish do have it. And this is, I would say, in a renewable future, this is mandatory, and this requirement will come everywhere in the long run. So this shutting down during a storm can't be tolerated, but at least it's a technical problem that's already solved, which is good. So this was the sweep through like the main requirements relevant for wind power. Just to wrap it up, today they're much stricter than they used to be in 2006, which is good. Wind power has become a big regular power source, just like other technologies, and it has to behave like other power plants. And strictness is really correlated to power plant size. We have to keep in mind single turbines, they get exempt from the strictest requirements, while larger power plants don't. But still today, even though these requirements are in place, the services are still mainly provided by the same conventional power stations that have done so in the past. But in the future, requirements will keep increasing in strictness. It's unavoidable if you want to have the renewable future, but it's also desirable, because we want a stable operation, so we have to have clear rules. And so this grid count process is still is ongoing. There is room for improvement, there's need for improvement, and at least from our side of the picture, especially the international harmonization, we can all just hope that this will move on, because otherwise it's really a hassle to deal with grid codes, because you need to read every country one by one. But this service provision, not just a requirement of the capability, but this actually using wind power plants to do something, not just ensure that they can do it, this will definitely expand. And to me, the good test lab is Ireland, because it's a small island with lots of wind power. So every time there's a problem, the best first step to the solution is how the Irish have solved it 10 years ago, because they're really ahead of being in trouble due to so much wind power. And by 2050, wind power delivering services to the system, wind power will be the system, at least at night time. And that means that we need to deliver the exact amount of active power, exact amount of reactive power which is needed in every second. And then where's the maximum power tracking? That has been really the focus for a long time, but in the long run, no one will care. We don't need maximum power, we need the right amount of power. So, and if you think any of this was interesting, or I was talking too fast and you want to read it, there is a nice review article which this presentation was based on. Nikos is one of my nice co-authors, and all of what I said and much more you can find there. It's a nice wrap-up of the relevant rules for wind power. Yes, I'm a bit over time, I'm sorry. So everyone who wants to ask questions has to speak really fast. Yes.
Your loss treatment, we need to balance it every second. What does it make the second and only the second?
It depends.
I mean, it's just a matter of saying, I presumably say it every second, but there is some kind of physical time scale.
Yes.
Below which we don't need to control.
And that physical time scale depends on the grid inertia again. We don't know where the grid inertia will be in 2050. What we know, it will be very different from 1 hour of the day to the next hour of the day, because in moments where you have low wind and solar radiation, hydropower will kick in, which is synchronous machines with lots of inertia. So will be like the easy moments. The hard moments will be when it's windy in the middle of the day, because then the wind and solar will produce more, will be capable of producing more electricity, which you could actually use. So then you have to already curtail, and then no one will run a hydropower and waste this water. And then inertia can go really down. And the lower inertia, the less time you have to keep your balance. And of course, also the solution is to buy inertia. And the Danish are very good. They just buy big chunks of steel and keep them rotating just to have the inertia. This is the, let's say, easy solution because it works. It's very approved, and there's no failure mode. If you just put inertia, then you have inertia, and it's always there.
But just for I on that, because a lot of these things depend on time scale, right? I mean,
yes.
Also, you talk about energy, but how are you kind of calculating energy? Are you going average over 1 minute, 5 minutes, 10 minutes, 15 minutes? That will be different type of control that you need to do. And maybe there's also big differences over Europe in that aspect. I don't know.
Not really, because it's all interconnected. And the larger the system is, then you like all the noise evens out in a nice way. So in a larger system, problems decrease in average. Also a reason why Ireland is more challenged than continental Europe. Yes, this is the critical things that define your time scale which you react on. And of course, if the inertia would be 0, then your time scale would be you would need to control infinitely fast.
But actually, there's some capacity. Is that not some inherent capacity in Europe? I don't know.
What do you mean?
Electrical capacity.
Oh, that doesn't really help. You mean the electrical capacitance, which is the field energy created by the. This is very short time scale.
Much more than that. Much more than that.
Much less. This helps you for, I would say, probably not even a millisecond. So this is the energy in the magnetic and electric fields. This is. No, we cannot take this into consideration to help us here. So in the end, it's the inertia. May be real, may be virtual, emulated inertia by control. That could also be, like either you buy inertia, buy big chunks of steel, but you could also just have like a battery with power electronics to behave like one. But inertia is what buys us time. But in the end, it's not much time we get, and the inertia is costly. It's not today; it's included in the power stations, but in the future, inertia will be costly. So being fast is good.
Building on that, how do you see? Because you have a demand side management. So you're saying that deliberately building in something with inertia, building something that's got kind of a usefulness as well as a large scale block is a large scale block, but if you've got, say, something like that, put a motor on the demand side, help you?
Yes,
Yeah.
they do actually a lot. I cut that completely out, but any inertia helps. It doesn't matter if it's a generator or a motor. So all the motors connected to the entire grid do help. Tricky part is just that 10 motors of 1 kilowatt have less inertia than one motor of 10 kilowatt.
Yeah.
And that means that power stations, few but large, have much more than motors tend to be very many small ones. So their inertia contribution is already much smaller than from the generator side. This is one problem. But it's not the worst problem. The real problem is that every day hundreds, if not thousands of motors get replaced by newer electric drives where the motor is decoupled to the grid by power electronics, just like the modern wind turbines. The motor guys, they have rooms like this where they sit and they just do the same thing. So also they decouple their rotating mass from the grid, just like the wind turbine. And
Even hydro generators are thinking about.
yeah, but they're still thinking. I don't think they have done it.
So you see that a market in
Yes.
to one side, or wind is kind of creating this. So there could be people that are basically just making their money by just selling inertia.
Yes. In Denmark, people sold chunks of steel, selling inertia, but also supplying the service. I'm not sure it will ever pay off to just build complicated system just to provide the inertia. But the trick will be that if you have a bit of flexibility and you have a power converter, you could do this at the side of what you originally planned to do. And they're placing batteries for frequency support in several countries already, a big battery with a power converter. And there is no good reason of how they could not also try to supply inertia. They don't, because there's no market yet. Because we're still used to that inertia is something we got for free. People build power stations and no, there was inertia. But this will not bring us to 2050. I hope the market will come. I don't know who was first.
Go ahead, but maybe a connecting point to the previous question.
Yeah.
Yeah, just following up on the inertia, because also the time scale. You were mentioning at some point like power inertia. A wind farm is obviously not possible if you don't first power fossil your energy, but that depends again on the time scale. Right? If you only need to do it for a couple of seconds, you probably can do it without prior powering down.
Yeah, this is the advantage of the wind turbine. It has a lot of inertia. It doesn't really support the grid because it's decoupled, but you could create the artificial coupling through control. That while grid frequency goes down, you slow down your rotor to extract the power. That has been researched quite a lot. I don't think it has ever been done. Someone can correct me.
Siemens has the initial response on the turbines.
This is the next trick part. They don't, but they say they do.
And they do.
Inertia response?
Yes, and it provides initial response. It doesn't provide the percentage they say. I have been the team that tested it, so it does provide.
Yes, it provides a response, but the problem is, as far as I know at least, it doesn't really provide inertia response. It provides something that is somehow similar to an inertia response, but it's not. It's always the question. If you, to me, a real inertia response is something that reacts to DFTT. Frequency changes and you go proportional to the frequency change. This is what inertia should do. And I think this really, like virtual inertia via hard physics, has not been implemented. But the function of inertia in a power system is to, when frequency goes down, that you need extra power to compensate for it. And this you can do by different means, by quite a larger variation of means. And I don't know the details of this. Maybe I'm wrong, but at least from what I've seen so far is that people have implemented systems that can support a grid, not by really emulating inertia, but by doing something that helps in a similar way.
Is that essential? Is the responding to
as long as you do have some inertia online, you can support that existing inertia by different means. But but these other support mechanisms that don't go hard on the FTT, they still assume there is some inertia and we just help it. But once the inertia is completely gone, everyone tries to help something that's not there, and then it doesn't work. So this is the grid supporting part, but you need still something to support. The grid forming is that you actually be able to do it yourself, and these mechanisms, they cannot do it. But also then it gets when inertia goes really to zero, then we have to change the converter control by several means.
I was about that journey to 2050 we can imagine that wind turbines will be at least 15 megawatts, if not bigger. I mean, do you think there could be a push to go back to type 3, to have some real DLT there?
I don't think so. I don't know. I really don't know. But I believe the advantage of type 3 is this connection of the rotating speed. But I would believe we must be able to get this done by control. Maybe not with the concepts which are industry practice today, but there is this concept of the virtual synchronous machine, where you don't try to measure frequency and then you calculate the FTT and you react on that, but you rather try to completely emulate how a synchronous machine would have behaved. And a synchronous machine doesn't measure the FTT. It doesn't measure anything, but it rotates and still has inertial response. And I think by such techniques, it should be possible to not emulate inertia, but to emulate a real machine or a type 3 machine. You could maybe even have a type 4 machine, which if you look from the outside and you measure the currents and voltages, you would believe it's type 3, but it's not.
Thank you. Could it be that in that situation, more than coming from control side, which is more could come from the overcurrent capabilities of the switches themselves, and from the design that would be perhaps the hard limit that the strategy is gonna hit?
Yes, that is always the very hard limit, the current limit. So then maybe it cooks down to an economic question. What is cheaper, to overrate the type 4 turbine and emulate the connection, or maybe to use the type 3 and have the real connection and not needing to overrate? That will it could just come down to an economic question. Also, price of the power electronics. Sorry, that was even, but he got totally lost. But
Okay.
To follow up the demand response, the demand side management. There's one thing is that they have inherent inertia as small motor, but also if all those small thousands of motors start pushing power during a fault event, when the grid is in very dangerous situation, maybe that's not ideal. I mean, there have been many academic studies and things like that. That's one point. Then moving back to DFIG, I mean, now we are only talking about inertial response, but reducing the converter side also takes away capability in terms of reactive power and other ancillary services you were talking about. So then you are again in that economic equation, you are putting a SCATCOM or something else to provide the reactive power. We should also consider the other economics of the other ancillary services.
yes. Coffee break.
No.
No. I know. Not at all, but afterwards we can continue.
Yeah. Which is much shorter now, I'm afraid.
Sorry.
That's okay. Yeah. There we go. 1 second. Just to make sure we're sharing the right screen.
Good afternoon. I'll try to save a little bit of the coffee break and be fast. My name is Peter de Kok. I'm working for ENGIE, the Global Energy Markets department since more or less 15 years. I have a past in the optimization of the ENGIE, portfolio of production and consumption. Today, I'm responsible for all TSO contracting and ancillary services contracting for a CWE area, so Belgium, France, Netherlands, and Germany.
Before you begin,
yeah, it works. So I'll talk today about market structures. I'll focus on CWE area and I'll focus on short-term markets. This is Europe. Europe is known as a synchronous area. It's a bit different for the UK and Ireland and Scandinavia, which are not in the same way connected as the rest of Europe. This is the physics of the network, synchronous area. It doesn't mean that the market is representing this in exactly the same way. It's important that the market is as close as possible to the physics, because that means that you have a much more efficient market. If in physical reality energy can be produced in the north of Europe and consumed in the south of Europe, then it's important that the market also allows that the current goes like that, and that people buying in the south of Europe are buying the exact electricity being produced in the north and vice versa. Why is it important? Because it makes that your market is much bigger. It makes that there's more buyers and more sellers, and so that you have more liquidity into your market. You can manage a cross-border portfolio, and it also allows for intermittent production to be introduced in the market in a much easier way. Today I'll talk a lot about organized markets, but of course electricity market in itself is much bigger than that. You have producers which are selling into exchanges their production. You have resellers that are buying in these exchanges the power that they then sell to consumers, be it household consumers, be it industrial consumers. But there's also direct contract between the producers and the consumers, and direct contracts between the producers and the electricity resellers. And you have contracts between the producers and the TSOs, and between the consumers and the TSOs. So electricity market in itself is much bigger than the organized markets, on which I will focus in the presentation. Market time frames in organized markets are going from more or less 3 years ahead up to real time. Meaning that you can today buy electricity or sell electricity for the year 2021 or 2023. If you want to make a contract for 2025, you will find a lot of difficulties to have a liquid market in this product. Doesn't exist. In forward, you can trade in yearly products, monthly products, up to day-ahead market, intraday, day-ahead, which is hourly contracts, intraday mostly, up to quarter-hourly contracts. And balancing markets being ancillary services purchased by the TSO, so managed by the TSO. What do you use forward markets for? Is to hedge yourself against price volatility. So if you're selling power and you know now at which price you can sell for delivery next year, then you're certain which price you will get for your production. Same if you're consuming electricity. If you can already fix now what is the price for electricity you will pay next year. For a lot of industrial consumers, it's very important because electricity is a big part of their cost. Day-ahead market is actually the market where that for classical production, the production plan is being determined. I determine today if my power plant will run tomorrow, yes or no, or the forecast I make for my wind production today, I'm selling it in the day-ahead market. So, or my best forecast, I'm selling it in the day-ahead market. Intraday is then used to adjust positions, going in towards balancing mechanisms where it's the TSO responsible for balancing the balance between what is injected in the grid and withdrawn from the grid, up to real time where that physics take place, because everything before that is just an anticipation of these physics that to take place, and so it's more financial. And you have exposed trading, so after everything has been done, you can still adjust your positions through trading, which is actually not about physical reality or financial reality, but which is about accounting. I produce too much versus what I consumed. You did the opposite. Let's exchange so that we're both balanced and don't get any penalties. That is the different market time frames. For every so like in every other market, how does that work in a market? You have an offer curve, you have a demand curve, where that both meet is the price for the product. And in electricity markets, you have an offer curve and a demand curve for every single point in time. So for a day-ahead market, for every hour that it's clearing, we have an offer curve and a demand curve, which is constructed out of individual offers. Generators offer their production costs. Buyers are bidding to purchase at the price that they want to purchase, leading to a price in the ahead for every hour. Of course, it was mentioned already, the electricity is a continuous process. So in principle, between injection, production, consumption needs to be balanced in a continuous way. Still in markets, we limit it to a discrete granularity. So in intraday, it's 15 minutes. In real time, we need to be balanced on a 15-minute granularity. Whether that we inject everything in the first 5 minutes and we will consume everything in the last 5 minutes within your 15. For a market, it doesn't matter. For the physics of the network, of course, it does matter. What are the roles within the market? We have balanced responsible parties. Those are typically producers or consumers and that have a portfolio. They're responsible for the energy balance between what they inject into the market, into the grid, and what they withdraw from the grid. Inject can be production or what they've bought into the market, or withdrawal can be consumption or what they've sold into the market. TSO is the one that is responsible for the physical balance in real time. TSO is not allowed to have any assets to make sure that the system remains balanced. So there will be purchasing services. From who? Ancillary services. From who are they purchasing services? From balanced service providers who are typically owners of flexible production means or flexible consumption units that allow them to sell this flexibility. These balanced service providers are not necessarily the same as the one who is responsible for the balance. It can be someone else. Then day-ahead intraday market. So how does that work in Europe? Day-ahead market is a zonal market with one price per zone. Zone usually equal to a country. One price for Belgium, one price for the Netherlands, one for Germany, a couple of prices in Scandinavia. So you can have more than one price in one country. Within one country, the price is the same. So if you're producing electricity in the north of Belgium and someone buys that and consumes it in the south of Belgium, it is one price. Of course, there's no constraints to transport it. Of course, in reality, there are some constraints, but as a market participant, you don't care. It's the TSO that will need to take care of that. Between several countries, there you have interconnection capacity between the countries, which is taken into account. And so if the interconnection capacity is saturated, it will lead to two different prices, one price in one country or one zone and another price in the other country or zone. And how is that formed? So it's you can have bilateral transactions, of course, in day-ahead, but there's one big, huge auction in day-ahead where a lot of the European countries are interconnected with each other, which is called the price control region. you have a little graph on that on the right and the bottom. So all countries in the same color are interconnected in the same auction with each other. Buyers will place their bids to buy in a given country. Sellers will place their bids to sell in a given country. The TSOs put at disposal the transmission capacity between countries, and there's one huge algorithm which will run between 12 and 1 in day -1, in day ahead, and give a price per zone. This huge, so that's what I just said, this huge, this algorithm which calculates all of that every day is called Euphemia. And you have specific kind of biddings and block biddings and very complex orders that you can make into this market, leading to clearing. As long as borders are not congested, price will be the same in the different countries. If the border is congested, it will lead to another clearing of the price, so a different price level. In your offer and demand curves, the imports, exports are taken into account, which will lead to eventual price setting in different markets. Day-ahead market, considered as market reference in a lot of situations, in a lot of contracts. You can have contracts between producers and consumers which are referring to the day-ahead price. Why is it referred to as a reference? Because it is historically the price at which units are being scheduled for nomination and so forth. Reality in the network is being reflected by the imbalance price contractually in the market. Day-ahead market price is usually referred to as reference price. Intraday markets are usually used to correct positions. Historically have a very poor liquidity, but which is something which is changing over time. And we will see that later on. Intraday markets, so while day-ahead markets have an hourly granularity, intraday can go up to quarter-hourly granularity. It's not one algorithm that runs once a day and then gives a price for every price zone. Actually, you have a continuous process in intraday, where that you have an interconnected market in Europe. You can place your bids in one country and another country. TSOs will put transmission capacity available as long as it exists, and it works on a first-come, first-served basis instead of one algorithm that optimizes the whole thing. Intraday markets, you can trade in one zone, so as long as you stay within the zone, you can trade up to 5 minutes before real time. If you go across zones, so if you need to cross countries, you can trade up to 1 hour before real time. Why are there rules there? For market participants that want to adjust their positions, they want to be able to trade as long as possible until real time so that they can be balanced in the best possible way. Of course, the TSO will tell you, well, after all of the market is done, I still need some time to look at the residual imbalance that I'm expecting and to be able to adjust to it. That's why up to 1 hour cross-border, so that everything is fixed between the countries, up to 5 minutes before real time within one country. And that is so for all of CWE at least. It can be different in other countries in Europe where that somewhat other rules exist. Short-term markets becoming more important. If you look here, in 2000, almost nothing day-ahead market up to now 2017 is the last graph, is 500 terawatt hours being traded in day-ahead markets. That's Belgium, Switzerland, Germany, France, Netherlands, UK. And intraday volumes, 2004, almost nothing, up to 70 terawatt hours in intraday. Where does that come from? That you have this additional liquidity in short-term markets? Well, it comes from renewable assets mostly, because for a nuclear power plant, you can make an assumption on what will it produce on average next year, and then you can sell that in a forward contract. And then day ahead, or in intraday, don't need so many deviations or corrections to come to your average production, to your real production. and if you take a nuclear power plant of 1,000 megawatt, if you do the same for a wind portfolio with an expected production of 1,000 megawatt on average, of course, and you sell that now for next year, the next year, every day, you will have quite some activities making sure that what is expected for tomorrow or what is expected for within 1 hour is being compensated versus what you sold 1 year ago. So that's one of the main reasons why that you have more volume, more liquidity in short-term markets. It also, we have better access to cross-border. TSOs are putting the borders better at disposal of the market. And you have introduction of automated trading. You have robots being put on that. For every change in the forecast of your wind turbine, is not a trader who's going to make a transaction. It's actually a robot that will take the difference and put it into the market. Much more liquidity in intraday markets. Here, that's the same. So this is the standard deviation. Is a graph from 2015. Standard deviation from 2 days before real time up to real time. Standard deviation of the forecast error. And you see that actually only 3 hours before real time, it really drops sharply. So until then, it changes a lot. This is the same. This is intraday markets. You see the 10 hours before real time, and you see that a whole lot of the volume is actually traded close to real time, and also a whole lot of in this period you have a lot of price volatility, because it's only a couple of hours before real time that you actually know, will my position be long or short? Do I need to adjust? Yes, no. And so you have a lot of volume and a lot of price volatility in the couple of hours before real time in intraday markets. This is a picture of intraday markets in Germany. So as I already showed, it is going a lot up. The volumes being traded in intraday. Doesn't mean, on the other hand, that forward markets are traded less. The average that remains the same. You can sell it in forward. In intraday with renewable assets, you need to adjust much more. So more liquidity intraday doesn't mean less liquidity in forward markets. That was that for intraday day-ahead markets. Then we go to balancing markets. And we already talked a little bit about that. So balancing market ancillary services. TSOs, transmission system operators, are responsible for securing the operation of the electricity grid. In order to do so, they contract services. They don't have assets themselves which allow them to do so. So they contract services. What do they contract as services? Being available for the system. This goes from just managing the revision planning of power plants within a year up to now more and more capacity remuneration mechanisms to ensure adequacy in the system, which are popping up in several countries in Europe. You have congestion relief, redispatch within countries, which is being contracted, balancing services, voltage regulation, and black start services. Black start services, if the grid has gone and shut down, you need a power plant that can start up without feeding electricity himself. And so all of these services, TSOs are contracting, so they're paying for it for someone to provide these services towards a TSO. If we zoom on the balancing services, you have different kinds of balancing services, and they vary from each other in terms of the energy which is required and in terms of the reaction speed which is required. So you have frequency containment reserves, which is a reaction within a couple of seconds, but which in energy is not a lot of energy to be provided, up to secondary reserve, automatic frequency restoration reserve, reaction within a couple of minutes, more energy is required, and manual frequency restoration reserve, reaction after 15 minutes, and which is a restoration reserve. Not all assets are, of course, fit to deliver every kind of reserve. It depends on the reaction speed you have and the energy that you can provide. And then these balancing markets and how they are structured in Europe, this is driven by European guidelines. And the European guidelines are driving all of these markets towards short-term tendering, meaning a day-1 tendering for our products, whereas in the past, historically, that used to be yearly contracts. So me TSO, I want to contract a balancing service so that I can balance the grid. Who can sell me that for the entire year next year? Now, and that is being implemented as we speak in CW, we have 6 implementation projects this year alone, going towards daily auctions for our blocks. And so that goes along with these markets being opened to new technologies. In the past, it was mainly thermal power plants delivering these services. Now, more or less, anybody, demand flexibility can deliver these services, batteries can deliver these services, wind can provide these services if they fit. And of course, to commit to today for tomorrow for a 4-hour period to deliver the service is something else than today to say, well, for 2021, I'm going to deliver the service the entire year long. Daily services means, of course, more day-ahead operations because it means you have a tender for the frequency containment reserve, FCR, at 8 a.m. in the morning, one for AFRA at 9 a.m. in the morning, one for MFRA at 10 a.m. in the morning, and then by 12 you have the power exchanges, the normal day-ahead auction. So there's a lot of operations being planned in a short time frame. Next to that, so that's for balancing service. Next to that, there's also new opportunities which are arriving in local flexibility markets, whereas it is not only the TSO who has some balancing needs or who has some congestion within its grids, is also the DSOs that require some flexibility services. And you see more and more local initiatives towards local flexibility markets arising, or even better cooperation between DSOs and TSOs to jointly procure flexibility services, which are not only localized within one country, but with a specific location linked to it, which allows also for DSO balance. Then the imbalance price, so all of these balancing services are measures that the TSO takes to make sure that the grid is balanced. All of the costs related to these actions by the TSO, they're reflected in the imbalance price. Who is going to pay for the imbalance price? The market operators that didn't balance themselves. So if you are taking more from the grid than what you injected, you will pay the imbalance price. This imbalance price should be dissuasive so that market participants balance themselves and that TSOs have less work to do. And of course, with more intermittent capacity, intermittent production, less predictable production and consumption, that's putting more pressure on the TSOs, more residual imbalances, and hence being mitigated by TSOs by putting more pressure on balance responsible parties. And you see a couple of recent examples in there, where, for example, in Germany, in the imbalance price, they will put a factor of the ID 500, which means that you will never pay an imbalance price which is higher than the price for the last 500 megawatt traded in the intraday market. So you have all interests to balance yourself in the intraday market instead of waiting the imbalance to happen. Similarly, in Belgium, there since 1st of January, they put an alpha component in the imbalance price, which can go up to 200 euro per megawatt hour, depending on the system imbalance in this quarter of an hour and the previous quarter of an hour. All in all, what did I say? Day-ahead and intraday markets are gaining traction. That is because of the energy transition, more need for rebalancing in intraday. Regulatory developments, making sure the markets are interconnected, and robotic trading. The increase in short-term trading doesn't mean that there's a decrease in forward trading. You have balancing markets which are opening towards known technologies, being contracted on a short-term basis in day-1 4 hours. You have new opportunities in local flex markets, and TSOs are increasing pressure on market participants so that they remain balanced and that TSOs have less residual work to do on their side. That's it. If there's questions. Yeah.
Thanks a lot. That was very good. One quick question. Right now, with the subsidies that we have on the renewable assets, we are not really so keen on participating in any of these markets, or we don't really calculate the opportunity cost to participate actively. If we go to a more subsidy-free scenario within the next 5-10 years, and also adding from the previous presentation about, actually I would argue about that one as well, regarding when we have the extra wind in the system and then the hydro would be the main party, which I would argue it's not the case. Do you have any way of calculating the opportunity cost if you have a subsidy-free scenario? Have you thought about how to calculate the opportunity cost to withdraw some of your production capacity and then participate in these ancillary services?
Yes, of course, and it's exactly the same that you do for a thermal power plant or for a wind production. The calculation is the same. So it's the production that you forego for upward, because here we're talking about upward services where that you need to forego a certain production to be able to deliver upward flexibility. And so for any asset that is providing upward flexibility, is the same. If you have a CCGT, which is providing upward flexibility, you will run below the maximum production, and so there's a delta. But you're very right. Today, in a subsidized system, it might be very expensive for wind capacity.
Yeah, I agree. But when for the thermal power plant, that was a very good example. Then we go back to the basics of the market structure, at least in East Central Europe, which is like marginal cost, defining everything. And that is, to be honest, that's not the right way of putting it when we have more than 50% renewables in the system. There's a lot of things going on about that as well. So would that be still the case if you want to calculate the opportunity cost for a renewable asset? Do you still look at the marginal cost? Because if that is the case, we have no fuel cost. Then how are you competing against the gas power plant, which gets a lot on the savings because you have fuel cost in their calculation. So they just jump on the opportunity cost.
But well, for a downward regulation for wind, there is no opportunity cost either. For upward, there is an opportunity cost, which is forgoing of selling your wind power into day-ahead markets or into intraday markets. So for me, the calculation is the same. Whereas you're right, is that if in systems where, for example, for the downward flexibility, and if wind assets don't have any opportunity costs at all, you have a risk if more and more of these sort of assets start participating in these sort of markets, that the capacity fee that you will get will go down dramatically. And hence, you should get all of your remuneration out of the activation. In Belgium, we will start this year in EFRAG, we will start contracting, instead of one baseload symmetric product for a whole week, we will start contracting 4-hour blocks, upward and downward separately. If a lot of wind producers say, well, the downward 4-hour blocks, well, this seems like something I can do, my opportunity cost in doing so is zero. So you might have some products, if a lot of producers with a close to zero variable cost or opportunity cost, the value of the products might go down a lot. On the other hand, if that happens in Belgium and then these products are activated, in Belgium you still have a lot of subsidized wind. So at the moment that it's activated downwards, then you will have less production, less subsidies. So your imbalance price, as a consequence of that, might go through the roof or down the floor. Because you need the 120 euro per megawatt hour subsidy to be recouped every time that you activate. So there's a balance between what's being paid for the capacity and what happens in real time every time anything is activated. And of course, nobody will continue to deliver a service if the economic picture does not fit, you know?
Yeah, fair enough.
Yeah, I have a different question or something I've not fully understood. So, who is paying for the imbalances? Because you kind of seem to mention that
it's the market,
but that's basically the consumers, I presume.
well, is everybody in the market.
Right.
So as a balanced responsible party, you're responsible to be balanced on your portfolio. If you're not, you will pay the imbalance price. The imbalance price is being determined by the means the TSO needed to activate to balance the system.
But it's perfectly possible that you are unbalanced, but that within the 15 minutes there are big unbalances that need to be evened out, right? I mean, you start with the example of everybody producing the first 5 minutes and everybody consuming the last 5 minutes. So that then nobody is out of balance, but you still need to have a lot of costs in terms of.
Yeah, but of course it rarely happens. It rarely happens that all of the consumption and all.
But that would be then to pay by the consumer, or how would that go?
But everything which is not covered, and that's the same for the procurement of the balancing services. So for TSOs to be certain that they will have enough capacity to activate in real time, in day -1, they procure a service. So for this service, they pay a fixed fee. The cost for this fixed fee is not in the imbalance price, so the TSO need to recoup what they're paying for it. Whereas you will find it in the grid tariffs. So, and that's the same with if the calculation doesn't add up between all the means that the TSO activated and what all the market participants have paid in imbalance price, it doesn't match up. The delta will go in towards the grid tariffs, and grid tariffs are being paid by consumers and paid by producers, and who pays what is in every country a little bit different. And of course, also, if as a balanced responsible party, you didn't balance yourself properly, you pay an imbalanced price, then also you're going to look at what is downstream. My customers didn't consume exactly what I predicted, so there is an imbalance payment usually in your or a prediction of what is the imbalance cost, usually also in towards the tariff that you ask towards your clients. Yeah.
I have one hopefully quick question, because you mentioned the local flexibility markets.
Yeah.
To balance the TSO and DSO and make them communicate. Do you have an example about the time scale what to be able to, like, is it going to be faster than 15 minutes, for example, or?
No, so the imbalance settlement period is 15 minutes.
Yes.
And the flexibility market is well, you have all kinds of experiments. The one that I mostly follow are the ones where the TSOs and DSOs are cooperating with each other, and then they're branched towards the existing wholesale market. So it means you stay within the secondary reserve or AFR kind of MFR kind of products, which have the same granularity.
Comment on the question, short comment about this determination of the opportunity cost. I don't think there's any problem. There is, I think wind power behind solar power is the number 2 where it's the easiest in terms of the opportunity cost. Because we don't have fuel prices, opportunity cost is basically what we would have earned by selling electricity. So it just gets easier compared to other sources, especially hydropower, where opportunity costs are really surreal.
Yeah.
So that is nothing we should worry about.
I don't think that is the case, actually.
Yeah, I also think we can debate that a little.
Yeah.
So I have a suggestion, let's do a coffee break now,
Yeah.
and let's start that debate during the coffee break. I would suggest to not shorten the coffee break, right? Just, we have still some time left.
Exactly, yes, we can still do that. So we can come back around 3:30, we can start moving through the course, and maybe we can start around 35 hours.
Waste some of the wind energy. And we completely neglect the demand side.
So when you didn't neglect it, I just couldn't talk about it because there's a lot of wind power.
There's going to be a huge opportunity for
Anyway.
Okay.
So good afternoon, everyone. So I'm Kaushik and I come from DTU Wind Energy, and I am a power system engineer. So I'm not a market modeler, and I'm very happy that Peter was very detailed about the market modeling and everything. And I come from the other end where Nicolaos and Til Kristian was presenting. But today I'm gonna talk about something about how it can be in 2050. And I'm not Nostradamus, so I don't know how the 2050 would look like. But also I have another role that we have a group discussion later. So this is more to frame it up and open that group discussion later, and it will be very broad group discussion what we have decided, because the people are coming from very different backgrounds. So the biggest question of the day, right? How the future European energy system would look like with massive share of renewables. And when we say massive share of renewables, I mean, Nicolaos was presenting that Wind Europe has this vision of 450 gigawatt by 2050 and things like that. So we see the major development in the North Sea region with really big machines there. So we are working in a project, ongoing Danish project, and the findings are mainly from that project. So what is the project? You can get the details about Infant DK, and I'm not going to talk more about that. But what is the role of wind power plant in such a large European system? And that's what we are trying to address in this presentation. And after, in the group discussion, we'll talk about what could be the role of wind power plant control in such a system towards 2050, which is the focus of this workshop here. So in order to answer what is the role of wind power plant, we developed a tool chain. So what it's sort of what Peter was talking about is, so we have a spot market model, and then we have the intraday model and balancing model, and then the rest of the imbalances are handled by the automatic reserves, be it FRR, FCR, and all those things, right? And they have different time scale. So this is based on the Danish way of operating the market and the power system. But we also have an intraday here missing, but the role has been very limited in Denmark intraday system, mainly because the fourth, okay, I'll come to that,
China.
So we try to model this, how it would look like until 2050, and so I'll come into details about all these blocks. So basically it is driven by this scenario, how it would look like towards 2050, and then we took 3 steps. We took 2030, 2020, 2030, 2050. So how we gradually move there, and this is a very open question, and everybody is trying there. But we started with something called NS-Kogi report, which is very widely acceptable, and then we try to criticize on that, and then because that is also a bit old, and so we have seen a bit more, and then we develop a bit more on that. So I'll talk about each of these components in my next slides. So I'll start with the scenario. So the main aim of this project is to model the North Sea region, and then you can see the similarities what Peter was saying, showing that they are divided into many market zones. And then the major question was that when the offshore wind farm are being deployed in the North Sea and also the English Sea, or however it is called, but this region, how they would be connected. And so we have taken 2 approaches. One is the project-based connection. That means every wind farm which is developed is connected to the shore, to the nearest location. And the other one is that you develop a offshore grid in the North Sea, and then try to connect them to the nearest shore. And then there are many political discussions there, and I'm not going into details, like if the Danish wind farm which is built near Germany, should it be connected to Germany or Denmark and things like that. But those you can find in details in the projects and things like that. But and then we also tried to look in briefly into the sector coupling, mainly the heating sector there. So what we do is basically we have some tool at DQ Wind Energy called CoreRes, which is able to model the spatio-temporal correlations about wind and solar in different regions. And this we also provide this time series to ENGIE for their pan-European climate database. So we believe they are also a bit. We have some confidence on them. And then we develop in Balmoral investment optimization, where we put all these regions and try to minimize the cost of the system. How do we move from this point to the next point with the minimum cost? And then we get the final scenarios in terms of what is the total gigawatt which is installed and what are the annual terawatt hour generated and things like that. But when we need, this is so computationally expensive, what we need to do is that we have to have representative environmental conditions represented there. So some weeks in the each season kind of thing. You cannot run it for 30 years, even though we have the 30 years of meteorological modeling in the behind, but it has to be representative. So then we validate this in terms of running unit commitment in for whole year or every hour, and then I will come to that. But this is sort of framing up the what should be the investment model should be in order to go to that place. So the project-based scenario and the integrated scenario, like I talked about, the project-based, all of them are just connecting to the shore to the nearest position, and then North Sea offshore mast is you connect them to the hubs, and then the hubs are being connected to the grid. So the resulting project-based scenario gives us around 92 gigawatt of offshore wind by 2050, and in terms of percentage, so we have variable renewable energy. That's, yeah, we are a bit strict about our definition. So this is not RES, this is the variable. So this does not include, for example, large hydro, which are not that flexible or not variable by nature. It's more controllable. This is wind, solar, and small run-of-the-river hydro and things like that. And in terms of renewable, we get around 88% in this model towards 2050. When we go to the other scenario, offshore, then we get increase in 39%. So the gigawatt increases 102 gigawatt, and then renewable increases a bit more. But this is without considering any sector coupling in the model. But then we include the sector coupling, and this is still ongoing work. So we do not have the complete transport sector, or we do not even have the hydrogen or gas sector yet in the model, but we have the heating sector, which is mainly the district heating, but also some heat pumps, and then we have the transport sector there. Yeah, mainly the power to gas is missing, and also transport sector is not modeled completely yet. So the early results what we get is basically towards 2050 we get up to 158 gigawatt of installed capacity, and this so significant increase in the electricity consumption with the sector coupling. So that allows us to go more, and then Ivan is going to talk tomorrow about this, but this 212 is the vision, and then we are reaching close there. And if we have more sectors, I think we'll be quite close. So we are not far off to the vision what Wind Europe has. So on the discussions of the scenarios, so we integrate offshore grid scenario shows a bit increase in the wind power, offshore wind around 10 gigawatt. But also we also see that the not very strong connection of this offshore grid to Denmark, because this project is mainly focused with Denmark. But sector coupling is increasing much more the potential of the connecting more wind. And this we'll get to see more as well later. And then talking a little bit about core-res, I think all of you probably know about core-res. So the core-res models for both wind and solar, but model future scenarios, the base, the underlying model is 37 years of hourly data covering the Europe, but also we have North Africa and whatnot. Now we are going at global scale. And then it can also simulate the forecast errors, and then we have validated those results based on some real case studies. But then now when we have the scenario, more or less, then we try to model the spot market day ahead model. So the reason is that from core-res we get the forecast 1 day ahead, and based on that you run the unit commitment for the whole system. And then when you get a better forecast, then for example Energinet in Denmark, they can deploy some manual reserves in order to mitigate the imbalances. So we are trying to formulate that and see how that is going to be impacted by 2030 and 2050. What we have seen that in general the forecast in intraday is not that much improving from the day ahead, because generally the weather model is not getting updated. It takes some time and things like that. Generally the intraday is mainly to handle if there is a sudden disconnection of a generator or something, then there is no imbalance going on to happen, and then intraday can be allowed players to do that. Also we should understand that this is marginal cost optimization, like Reza was mentioning before, and then this is not also in practice you will see that many wind power plant owners are mitigating their imbalance through portfolio management, and that's what we are not modeling. But in any case that does not changes the conclusion, because either you buy it from a market or you have your preferential partner to mitigate the imbalance stays there, which is naturally coming. And so our assumption is there that all in 2030, 2050 scenarios, the forecast remains the same. In case you get better forecast in the day ahead, much improved forecast than today, then this imbalance would come down. But assuming that the forecast technology does not improve that much, how is that going to impact in terms of the other markets? And then we can discuss later that what wind farm control or wind power plant control see opportunity if you need to play in those markets then. So without sector coupling, so this is how the after we have run the day ahead optimization for whole year, what we see is that how coal is being replaced. So this black is the coal and how it is being replaced by 2050. In general, the penetration of wind and solar replaces most in the fossil fuel, but not completely. We still have some left and also some nuclear left there in the system. With sector coupling, so we co-optimize the electricity and the heat sector. So it pushes the wind production. So this is sort of validation what we did with reduced set of the environmental data. Now we have whole year run and this is giving us more. So we have the unit commitment constraints, like you cannot shut down a nuclear power plant for a few hours and things like that. With those constraints, how your assumptions are still validated. Then we look at the curtailment, and then it becomes interesting. And what we see that we have substantial increase in curtailment, because either the demand was not increasing towards 2050, or there were hours when you did not have enough demand, or the transmission system was getting congested in those hours, or the unit commitment constraints that you just cannot shut down a power plant, be it nuclear or hydro or whatever, and then you have to run it at minimum. So you have to reduce the other generations. But even though increase in the number of terawatt hour is increased, but the percentage wise it's not that high, it's still 6% of the curtailment. Then we wanted to look when is the curtailment happening, and then we see 3 peaks here. So these two, okay, you can couple them together. That's the winter peak. You have much higher wind. but also the summer peaks is because there were much low demand. So it's widely spread. So it's not very clearly coming into saying that it's only the winter. When we introduce the sector coupling, the curtailment reduces 90% because the demand suddenly increases. So that is the value of increasing the demand into the network. So instead of electrical demand, we started putting in the heat demand and other kinds of demands. So then suddenly this started making a big role. Then we started looking into different regions, and I think Peter was mentioning that different regions have different prices. Since we are doing the system optimization, so it is a bit expected, but we have also the transmission constraints and congestion into account. We see that there is very much harmonization happening, and this is a very ideal market situation. In practice, there will be some non-idealism there, but you can see that they are very much getting standardized towards 2030 and 2050. Another very interesting thing is that the prices increases by 2030 and reduces by 2050. The reason for that is our assumption in terms of carbon tax. We assume that the carbon tax is more increased towards 2030, and then that starts putting more renewables, and then when you already have renewables, then carbon tax does not play that much role. So, of course, these are based on the assumptions, and we do not exactly know how the value should be, but in general, it gives a good picture how it could be. Also, more importantly, we have a setup now, and then you can already play with new numbers and things like that. In terms of variability of electricity prices, the volatility of prices increases much more towards 2050. So these two are 2030 and this for 2050. So many high amount of hours with very low prices you get to see by 2050. In terms of correlation between the prices and VRE penetration, this is also very interesting to see that when the VRE penetration is very high in 2050, the prices is so correlated in terms of prices and VRE penetration. So today the wind power plants are price taker, but towards 2050 they are the price maker, and that's the why we should move beyond LCOE and beyond AEP, because you are setting up the prices in 2050.
This simulation to see where is this break point of going from price taker and move to price maker. Is there a percentage of penetration? We say, okay, from now on,
no, because it's very difficult to have. So what we have basically is 3 snapshots of the world or the North Sea regions, 2020, 2030, 2050. It's so computationally expensive to go from 2020 to 2030. With the sector coupling, so with sector coupling, the volatility again reduces very much. Again, then we start again seeing that there is another market player coming into the picture who has a big role to play, and then that allows the wind power plant to have number of hours when the power prices is not that low. So discussions on spot market model, that offshore grid scenario increase a bit wind power plant with offshore gigawatts and decreases a bit solar PV and wind onshore actually in the offshore grid. But sector coupling, which is the more interesting part, is that it increases the penetration of VRE massively. And when sector coupling means flexibility basically. So then we start moving into the other part, which is basically balancing. So the idea of balancing is that 1 hour before the operation, you get a bit better forecast, and you know that what you had committed in the day ahead market, and you can see the imbalance, and then you get an opportunity to rectify that imbalance. And let's try to quantify what that imbalance is, and then the discussion could be that instead of 1 hour, it could be 2 hours, it could be 10 minutes, and different markets in the world play in very different way. In Australia, it's completely real-time kind of market. In Denmark, this is developed, this is controlled by the ENGIE net, and then For example, probably in Germany, also in Belgium, they don't do anything, and then they have much more reserves there in order to handle it in real time. So they're not acting proactively, right? So this is basically acting proactively, that you assume this is gonna be imbalance which has to be handled by in the real time. So you take some action. So just to, because the numbers would look very weird or bigger for different regions, just to show that how different countries we are looking into by 2050 in terms of the penetration. So Germany is playing the biggest role, and that's also we are seeing that Germany and UK are the major consumer towards 2050, and then Netherlands, Denmark, and Belgium, they are the major exporters, and towards 2050. That's also our simulation source. But when we look at the day-ahead imbalance, what we see that significant increase in terms, for example, P95 values. So from 6,000 in 2050, there is 10,000. The P90, so that much imbalance you are seeing at the hour ahead. So when you are bidding based on hour ahead, that much imbalance, it could be caused 95 percentile of the time. So this is the value. You can think about this is the value of balancing. If you don't do balancing, this has to be handled in real time, and then if you do balancing, it reduces. When we look at the curtailment, so this is without the sector coupling, but the thing is that the curtailment, most of the curtailment is happening at zero prices or very low prices. So opportunity cost, I think somebody was talking about, and then the opportunity cost might be very low in such scenarios because the prices of the market in itself is low. And then all the discussion, how do you calculate how much, what was the available power and possible power and what not. But that's different question, but in itself it is decreasing. So that's moving towards that how do you shift this curtailment, and probably including storage, hybrid power plant or whatnot. So that's something we can also discuss in our discussion session. After we do the hour ahead imbalance, so I think the numbers are probably not correct, but we see substantial reduction in the hour ahead after we do the hour ahead imbalancing. I think the numbers are correct here. And then the remaining has to be handled by the area control and the frequency control, the dynamic controls. And then what we did here is that we quantified the requirement of restoration reserve just to hand. In practice, you will have also imbalances caused by other sources, and like load imbalances, the grid faults and things like that. That can reduce the overall imbalance or increase the imbalance. So they are not necessarily correlated. Some of them are correlated because if it is temperature dependent load, they are driven by the same weather, but not everything is correlated. So that's a difficult problem in itself. But this is what is the imbalance which is coming from the renewable energies, and then we try to quantify how much restoration reserves you will need in future, and then you can see there is sort of exponential increase in the requirements, and that's because also in many places this is done in terms of some empirical methods, and then we use probabilistic method to handle the imbalances. So we require much more FRR, restoration reserves. But even with that, the hours, the FRR is getting saturated. So you are dimensioning much more, but still your FRR is getting saturated many hours in these regions in 2030, 2050. And remember that these restoration reserves and containment reserves, they are mainly designed to handle the faults and uncertainty. This is uncertainty in the forecast, but still with certain certainty, right? You can quantify the uncertainty with certainty. So the rest of the faults or other things are completely uncertain. So if all those FRR is being utilized by your wind power, in future, then your grid security is also being compromised. Then also in terms of FCR, what we see that so they have a band of plus minus 50 Hz in continental Europe, and they want to stay inside there. We see that the frequency quality is gonna decrease quite a lot if you continue with 3,000 megawatt of FCR what they buy today. That's the frequency is going beyond this band, so you would see more frequency fluctuations. Maybe that does not necessarily qualify it as to be an unsecured system or something, but at least we should start rethinking in the sense that we do not need to probably constrict our frequency that close and have a very stable system and make our change in our mindset a little bit. So that could be another solution, or other solution is that buy much more than 3,000 megawatt, which is very expensive reserves. So discussions, again, the prices becomes more volatile in the day-ahead market. Balancing market plays much bigger role towards 2050, and then the frequency quality might deteriorate towards 2050, and then the activation of FCR reduces the security of the power system also, because this is much bigger problem, that this 3,000 megawatt of FCR, which is being completely eroded by the wind farm uncertainty. Then fault happens, and then suddenly the blackout kind of things can happen. So that's much bigger challenge. So what's next? So this is to set up the discussion we are having in the discussion session. Maybe we can take few questions, but maybe after this slide. So wind, maybe value of wind is beyond AEP and LCOE. It's not maybe, I'm quite certain, or maybe I'm opinionated, but I'm quite certain that that's beyond AEP and LCOE. Opportunities in different markets, spot balancing, ancillary services markets that we have seen that the role they are going to play in our model at least is much bigger as it is today. Sector coupling changes the whole scenario, right? And so, but when we say sector coupling, it can be different things, that some sectors are being developed in parallel, like heating sector, and they connect electricity sector, like decarbonization and whatnot they call it. But the EV is coming and replacing the commercial normal vehicle. But then there are also kinds of discussions to power to gas, power to hydrogen, and also creating offshore kind of hubs. There have been discussions, I have been listening, and that in offshore, far offshore, you can have offshore wind power plants, and Meyers fleet can go there to charge their fuel from those offshore wind farms, which are not at all grid connected in future. And that's one kind of sector coupling if you want to decarbonize, for example, shipping fleet. So does the wind farm control of objectives change in such a scenario? What do we think about that? Hybridization, if you want to shift the energy arbitrage, I mean, 1.2 gigawatt of hybrid power plant, utility scale hybrid power plant was built in India a few months back, and just I read today that they have decided. But the requirement for the tender was very rigid and very complex, in the sense that they were asking for farm power. So one day before, there are two prices, one is peak prices and non-peak prices, and one day before, the TSO and DSO just call you up and say that tomorrow from this hour I need this much farm power from your wind power plant or renewable power. And then you have to take in all kind of uncertainties and everything there in order to bid in that market. But so very different kind of controllers are going into play, and then maybe you can have a supervisory control where you are talking with different wind power plants, or there's this concept of cluster controller in offshore where you have multiple wind power plants, and then there is this supervisory control which is talking to different wind farms. But even within one wind farm, you can have a supervisory control which talks with your wind turbines, wind power plant, storage, or solar or whatnot, right? So there are the control interactions that also increases interfaces increases, the control loops increases, and Nikos was showing that when you have bigger rubber bank kind of power plants, anyway there is much more control interfaces and then the SCADA requirements and whatnot, together with grid code requirements. So what we need is basically need to model the specifications of wind power plant control for such futuristic systems. And that's what we decided, and that in this discussion forum, we'll try to brainstorm on what could be the objective for different revenue streams and what could be the input, output, and assumptions for such a controller to design. So I'm open to some questions. Yes. If we don't have questions,
I have a question about the modeling. A bit about the mechanics, how you have implemented the sector coding. You have mentioned it a number of times, but you haven't mentioned whether it's generation with heat, generation with transport, and then how much cross-coupling have you considered, or maybe you have missed that part?
Yeah, I have not put the numbers. I don't remember the exact numbers, but in the sector cup, yes. So we have the heating sector there in the sector coupling. So we have the industrial heating there. We have the individual users which are connected to the district heating in all these sectors, and then the shares of different heating solutions. We have some electrification of transport sector. It's mainly not the commercial vehicles. It's mainly the small vehicles who's being electrified. But this is ongoing work, and then there is a parallel project. One is Flex Forest. There is a Nordic project, Flex Forest, who are looking into detail. But there is another project which I cannot remember right now. This is done together with another department called PQ management, and they have been doing very detailed.
Are you playing with the numbers? I mean, in terms of how much coupling is there towards transport?
Yes, we are already writing some papers now, which will be published very soon. But some brief overview you can find in this article. What are the exact numbers we have in the assumptions? So we have two discussion topics, and we intend to spend half an hour kind of each, like 25 minutes each, and then wrapping up. So we intend to have 5 groups each. How many are we?
Maybe 4, but we can make it like this.
Yes. So,
but we can have about 6-7 people per group, so we can have like 2 at the back, and so we can't.
yeah. Yeah. So where are the sticky notes?
The
Yeah.
So maybe one brief comment. You have received a sheet like this for tomorrow. So please make sure that you put it away, that you can get it out back tomorrow, because we don't have any other copies. Okay. And don't use it now for.
So there are no copies, just a donor copy.
Okay, yeah, but for those that have this already, please don't use it.
We have 4 people here, so maybe somebody can join.
Yeah.
This is becoming very heavy.
Yeah, exactly, that doesn't need to. Can you maybe take
Just from a logistic point of view, I think it's going to be quite noisy if you don't talk. Can you just maybe move out and...
That's complementary, no? Yes.
Yeah.
By the submission, also need to get some copies before we start. Yeah.
I would propose if you like idea that we step outside. So
Some pressure as well.
Yeah.
well, exactly, and then we
Yeah, so maybe before you go, let's go over to the discussion topics. So just like Kaushik mentioned, what we want to have is basically pretty much this, what it might look like for the wind farm control scenarios in the future, right? So the vision of the topics is one, focusing on the inputs, outputs, and assumptions for certain scenarios, for certain objectives that wind farm control can contribute to. And there are some food for thought here. So in terms of inputs, what kind of inputs do you think will be more required for wind farm control? Time series, if it's a time series, then what will be the time scale, for example? We discuss a lot in terms of the markets. And then for the outputs, what is to be expected, what is beneficial to have? Like, should we go more maybe at the IRR levels, internal rate of return, in terms of the revenue? Or should we stay with the AEP quantification? This is more for the wind farm flow control people. So, and then the assumptions is, what are the current assumptions if you're focusing on the 2020 scenarios or 2025? And what are the future related assumptions? And there are some examples over there. So considering different turbine technologies, newer flow control concepts that might come into the picture as well. So that's one future looking discussion group. And the second one is the objectives. So how to maximize the revenue for different markets. It could be in terms of power production, it could be in terms of structural load management, lifetime extension, so on. You can also discuss operational versus design considerations and maybe how they differ when you think about the wind farm control in 2030, 2050 scenarios. And how does the forecasting and the wind farm control can or should work together, because that will be much more relevant if we're talking about dynamic market scenarios, because we're doing day ahead biddings or 15 minutes ahead biddings, so forecast comes more and more to the picture. So those are two different groups. One is for objectives. What kind of objectives do you think wind farm control can contribute? And the other one is, what are the inputs, outputs, and assumptions to go to those objectives?
It's 10 for 4:10, and then we meet at 4:35 maybe.
So one more question. So what kind of output should we generate when we come back? Should we have in our hands?
Yeah, the sticky notes, and then we'll just collect the sticky notes here, and then you guys move to the second discussion forum, and we try to summarize, and then after both the discussions, we'll try to summarize to the whole audience that what we can.
So what is the ideal number of sticky notes?
Well, it would be really cool if you can come up with 2-3 scenarios for a group. Then maybe we can actually see many of them overlaps, then we can have a winner. Like most likely output scenario that this group can foresee. Certain objective, input, output, and assumptions to go to that objective.
So we are doing the discussion one now, right? Everybody is doing the session one, right?
Yeah, well, they can also go hand in hand. Whichever one they want to start with. Maybe starting with the objective is easier.
Okay.
Think about the assumptions to go there, yeah. Okay. Maybe we should have also clicked the
Can we change this?
Yes.
Yes.
For the groups that are planning to go outside, remember to take some pens from the tables. Okay. If you don't have. But let's make sure. We'll be going around and some long discussions. But let's see, try and see what different groups have discussed. I think you all chose a presenter. Is there any volunteer who wants to start?
I jumped into to be first because we don't have actually we don't have anything. So, as a result, I will not be embarrassed to follow up on somebody who has like a nice. We just had a very extensive discussion. I mean, anyway, all I can say. So I think the discussion resolved a lot about what level of wind farm control is necessary. We have been talking a lot from the perspective of, I think, the weight and the turbine and the scale of how fast the turbine responds to things. So we're talking about power electronics, which we presume to be much faster than what you can see on that level. There was nobody in our group on power electronics. So our timescales to our feeling, the fastest things that happen is like 0.5 seconds or 1 second. With that, power electronics is milliseconds, so they can do everything instantaneously for us. So again, what type of wind farm control is necessary? And so we kind of talk about two types of control. One is what we would say the simple control, which would be obviously you need some control at the level of point of coupling to the grid, where you kind of provide what the grid is asking or what you want to give it. And then you just simply distribute without anything smart to every turbine the same thing, and you have a PI control that keeps everything on track. That is what we would call the simple control. And the question is then how much would more complicated control that includes wakes and inertia and all these kind of things, what is the value of that more complicated level? And we don't know. So there was a lot of discussion or ideas about, okay, loads and lifetime extension and O&M reduction, which we all believe from a fundamental point of view is probably interesting. But at the same time, we did not, I mean, at this moment, we don't feel there is any means to identify the potential benefit of that, or it's not even quantified what reducing the economic value of that would be, or, you know. So even if you give us a market scenario that would say, like, you know, this is the way the price is going to evolve, it's not clear how, like a more complicated controller, where you say, oh, and you are able to reduce the loads by so many percent in a certain way, how that would basically be important in a market situation. I think that's probably where there's still a very big research gap. That's where. Is there anything that the other guys want to add here?
I think one of the things we were saying about the kind of but the fact that a lot of the drivers come from a grid level rather than from kind of a opportunity level, so to speak, being more a case of the grid saying you've got to do this in order to be connected. Maybe not, but that was just like a general feeling on where these where the wind farm control opportunities would come from. And then, as Johan's saying there, you could perhaps solve these problems in a variety of different ways, and it's just that the difficulty of saying, well, you can solve them with wind farm control, that gives you some added value, but we can't quantify it in terms of money. We can't tell you how much money that is. And that's an area that needs to be looked at in order to help things through the future. Because there's a lot you can do, but it's just lots of stuff that's interesting and loads go down, and that's hard to sell.
There was maybe one additional thing that in this discussion, like maybe you don't need to have the value itself, or at least not an intermediate stage, because we were referring back to the Siemens controller, where we were kind of saying, like, you know, they're almost selling a belief rather than science, but nevertheless, maybe people that set up a farm, they buy the belief and go to the bank and sell the belief to the bank and basically get a better loan, so that may also be some value in the silicon, but in any case, that's also part of the requirement. At least in the immediate stage, push wind farm control beyond the simple control.
Following that point, there's at least one developer developing wind farm based on a 25-year life. It's what they're being supplied with by their OEM, and all their economic case is built on it lasting at least 30 years. And so they're getting their economists just put 5 years in their spreadsheet. I see we've got that from somewhere, but basically their idea is that lifetime extension is kind of a thing. we reckon we'll be able to do that and extend its life further. But again, making that on a case is very difficult. But it does need to like pulling into that belief. Just because people think you can do that. And so because they think you can do that, you can kind of sell it. But from an academic perspective, that's not that'd be very rigorous.
That's where we are.
Thank you, though. I see some notes. Who wants to go second?
Yeah, so in our group, we kind of deviate from this discussion, and we ended up talking a lot of very interesting things. And we first started to talk about some kind of storage and hybridized pumps, in which you will have both wind, solar, and the kind of storage system. And that will allow you to kind of operate your wind farm as optimally as possible, because you will benefit from the storage system to give more power in the case of the low prices. And you can also then combine that with solar to always produce as best as you can and reduce loads on the wind turbine whenever you have like maybe more solar power and reduce the output of the wind farms. So that was the start of the discussions. And then we first talked about how this could be linked with forecasting, because if you have more different renewable energy sources, then it's easier to achieve what you've been forecast the day before to the bids on the power markets. And then wind farm control gets interesting because this gives you more flexibility to achieve this forecast. If you are like a bit below what you have been forecast, you can increase the power production thanks to wind farm control. And in the other way around, if you're too high, you can curtail the wind turbines in order to reduce the loads and still give the exact value of what you have been discussing. Another solution would be also to do some sector coupling, for which you can see that the providing heat instead of electricity would be a kind of storage of the extra electricity. So using the heat as a kind of new storage system rather than just batteries. And yeah, for that, you will also need some incentive to do that and reduce the cost for combining heat and electricity. And yeah, finally, we discussed about how those big wind offshore wind farm would be connected to storage system offshore or onshore, and we concluded that it would probably using onshore grid storage systems before the point of connection with the grid. I don't know if I've been missing something. I think that's basically how the discussion went.
Thank you very much. Who wants to go first?
I have another black sheet of paper with the speakers. And you can be at the end of the discussion. So, we spent quite a lot of time trying to figure out what question we were trying to answer. We had a very interesting discussion. But I have to summarize that. Just opinions. First of all, there's two very different things. There's the weight control, which everyone's familiar with, and there's the more electrical side, which is fast frequency response is much faster and hardly interacts with the weight control in some ways, other than the fact that if you understand the weights, you will know better which turbines in your farm will be able to respond in time and so on. So there is a connection that way. We were fairly clear that annual energy production isn't the only thing in it's important here. The loads are going to be important. Depending on how things pan out, loads could be more important than AEP, especially if your wind farms will be curtailed a lot of the time. Matters, loads could be more important. Understanding the loads is important. So if during the life of your wind farm, if you're monitoring the loads, keeping track of them, then in 20 years' time, when you want to know what to do with your wind farm, do you want to carry on maintaining old turbines, or do you want to sell it to somebody, or do you want to extend the life? The more you know about what the wind farm has been through and what each turbine on the wind farm has been through, the better the decisions you make. But actually, day to day, even what we're doing, we're making decisions all the time. I suppose it's a bit like modern predictive control, isn't it? You make decisions today based on your assumptions or best guesses as to what's going to happen in the future, what the prices are going to be like, what the value of an old wind farm is going to be in 20 years' time. So you're making decisions today. Your wind farm purchasers are talking to your OEMs and trying to decide what sort of wind turbine to buy, what sort of wind turbine they'd like to buy, and the OEMs trying to decide what wind turbine they'd like to sell. And these decisions are all based on perceptions of what might happen in the future. When you come to a commercial deal where you weigh up the odds on both sides, and you make a decision, and then in a year's time you might make completely different decisions based on different perceptions. So, yeah, what are we trying to actually say here? Any big points I've missed here?
So maybe I think you summarized very well. But basically, I think you say that our figure of merit that we try to optimize might change over time. But that's fine because mostly controllers have this tuning knobs or factors that you can play with.
Yeah,
but if we were trying to, I think we were also trying to identify whether there is anything that is missing today in the current technology that is fundamentally missing in order to be able to get there.
That's right.
And maybe we say more or less no, because I think, of course, we can improve our understanding of wakes, we can improve the way we manipulate wakes, we control wakes. But in the end, we haven't seen something clearly from the discussion that we had today that was mostly based on the lead aspects. We haven't really seen any additional extra constraint that is coming to wind farm control. Something that are completely unable to do that, right?
That's right. So if for wind farm control, if you're wake control, for example, I mean, we're still developing it, so we get to all those better methods. But in 5 years' time, we can change how we're doing the wind farm control software. So we can adapt as we learn more and understand better. But the important thing, if we're buying a wind farm today, is that the hardware of the turbines has enough capability to do what we think we might want to do in the future. You know, if our perception is that we will need to do a lot of fast frequency response in 10 years' time, then maybe we want to ask the OEMs if they could push up the capabilities of the power converters to allow us to occasionally suck a bit more power out without burning them out, or whatever. It will cost a bit more now, perhaps, but if that's what we think would be important, that's hardware, and it's important to get the hardware right. Well, the power converter can be upgraded, I'm not sure.
A bit about the instruments, right? The monitoring instruments.
Yes, monitoring instruments. So again, keeping track of fatigue is important. So if you've got load sensors or whatever technologies, AI even rather than sensors, if you think you can do it that way, but something to keep track of loads. But also, I mean, simple things like if you're going to do wake steering, then
Your wind vane has to be capable of doing so many turbines now have nodding wind vanes that are not good. It's easy enough to swap it out for a nice. Yeah, that's hardware. That's a small thing which can easily be changed. But important things like what solidity your rotor has, what power density, it's a bit more difficult to change.
So the main focus then was the objectives going to be different because of the feature, but not necessarily the inputs and outputs.
Objective, there will never be one single objective, and this might evolve over time.
Yeah, or the weight of the objective.
Absolutely.
The preference of why to implement unified control to begin with, but the methodologies, might change. But decisions might also, it also depends on conditions. Yeah.
And basically, the turbines available today could all have all the capabilities that we're likely to want, and if you ask for them. There's nothing really new needs to be invented.
Sounds like a mature technology. And then the last one.
If I heard other summary, I think we're the most business-oriented guys. But that's okay, I think. So I will start with the output. What do we think that the output is in short way? You could say we want to produce the energy when it's giving us the most revenues, right? So we don't want to produce if the prices are negative, and that's a good start, of course. And if we are curtailed, we want to do it as efficiently as possible and distribute the power through the turbines so that the load and the stress on turbines is low. And we want to comply with the grid code, of course, and deliver ancillary services as possible. What do we need as an input for that? We need the voltage and frequency at a high sampling rate at the PCC level. So we set 100 Hertz something. So we don't think it's already implemented in the wind farm controllers today. Not necessarily. Of course, power and reactive power measurements at PCC, of course. If we want to react to energy prices, we need, of course, the energy price as an input. It's quite logic. If we want to know which headroom we can deliver for ancillary services, when we are curtailed, we need a wind forecast. It's also quite logical. And then, if we want to decide which turbine has to produce which power, if we are curtailed at a certain moment, we need, it would be ideally that we have a sort of health index per turbine, so we can deliver the power or choose which turbine has to deliver which power. That's also something the wind farmer can decide. And also, when we saw, of course, the example of Siemens, you need the yaw positions per turbine, so you can take wake steering into account to produce as much power, not as much power, but the wanted power as efficient as possible. So yeah, produce power when it's delivering the most money. So AEP is not relevant anymore, so it's not producing as much power, it's producing power when it's relevant, and producing it at a manner that it does, that the stress level in your wind farm or per turbine is as low as possible. Very short to.
Thank you so much. But the general summary of the discussions, which I will so far I'm hearing is a lot of people. So there is some convergence, what people have been discussing, see the main effects of how the market scenarios in the future is going to affect. How the zero subsidy era is going to look like for wind farming. The objectives are going to shift a little bit more towards the value/revenue level. How to define that, we don't necessarily know right now, but they will fix. There is a convergence or a consensus about that. And need for better sensors and wind farm control going hand in hand with forecasting and condition monitoring, digitalization techniques is also discussed. Another consensus. Are you right? And what am I saying? Oh yeah, so the effects of the hybridization and storage to wind farm control is also going to be at the objective level, not necessarily changing how we do wind farm control, as you see today. Let's talk about it again at the end of the project, but so far this is what we think is going to happen. Yeah, so for tomorrow, we are coming here, we're starting at 9, right? We have a coffee maybe at 8:30, was that what we had in the program?
Yeah, there's morning coffee.
Yeah.
8:30.
And today we also have lunch at 7 o'clock. Did we have a sister?
Late lunch. So there is one dinner for everybody. There's a couple of people that sent their dietary requirements. I hope the restaurant is taking into account. She sent it to them. But if you are not that person, if you did not send anything, you just take the general meal that I selected. I hope you don't kill me afterwards. Yeah, and don't forget to bring your badge as an identifier for what they will do.
Is it at 7?
It's at 7.